Hello, everyone.
And welcome to Data at Scale. My name is Maor Kleider. I'm a director of product management, supporting the product management team in the data info organization, working to enable the company to make data-informed decisions and solve some of the hardest problems in the space of AI, analytics, monitoring, and privacy. And together with me, we have Yelena.
Hi, everyone. My name is Yelena Piashevets-Grbovic, and I'm engineering director in data infrastructure, supporting real-time systems team. The team responsible for bringing a fresh data to all the meta services and the applications. And I'm thrilled to be with you today.
At Scale is a series of technical, educational conferences for engineers who want to learn about the biggest challenges and opportunities that touch systems at scale. Today, we're going to delve into data. Data is really the secret sauce that enables companies to develop products with empathy for the users, to identify market trends, to keep their services up and running, and way, way more. I'm so happy to learn from companies like AWS, Google, Razorpay, MotherDuck, Snowflake, and from our colleagues at Meta.
And to kick it off from Meta, we will hear from Barak. Barak Agur is an engineering leader supporting data infra. He has been with the company for 7 years, tackling some of the hardest problems in data infrastructure. And today, we will learn what it takes to build AI-first data infrastructure.
Hello, everyone. I'm excited to be here in our third Data at Scale event. It is amazing to be speaking to so many industry leaders. I'm Barak, and I support Meta's data infra teams. That means I wake up every morning thinking about data, and I finish my day thinking about data. And yet, with the crazy evolutions going on in the data space, not a single day looks the same, and I'm always learning new things. Today, we thought we will bring some of that excitement onto you, and especially focus on the AI data-driven infrastructure. We will do a quick recap of where we were in 2022, our last Data at Scale event, where we are now in 2024, and we'll follow with where we believe the next set of challenges lie. And if this tech discussion sounds a bit too tech, I'm excited to share that later in today's program, you will also get to hear from DJ Patil on how do these technologies touch all of us in real life. But first, let's talk about how we got here. In 2022, in this exact event, we put a lot of focus on the AI ML revolution. And our partner Amani, who was doing the keynote back then, talked about the massive change in this introduction. These days, it feels like that was an understatement. We're in the midst of navigating a generational shift. It is truly one of those inflection points in the history of computing. This might sound a bit hyperbolic, but believe me, this is a great time to be working in tech and in particular in the data space. To put things in context, I want to talk about some inflection points in the past and some of the patterns we've seen when we see new technologies emerge. There has been a series of maybe 5 or so major transformative milestones in the history of computing. And I mean major steps, among thousands in between. We have to start, obviously, with the transistor, the most elemental part of the logic circuits. This is the first transistor, from 1947. It replaces vacuum tubes and more cumbersome switches, relays, and amplifiers. We would now miniaturize and make a lot of technology, like TVs and radios, more reliable, cheaper, and obviously smaller. It laid the groundwork for novel applications like advanced logic and computing. The next major innovation, and this is admittedly skipping ahead a long time and a lot of innovation, which gets us to the next major computing leap, is the personal computer. The PC jumped us ahead from large mainframe computations to more advanced programming. PCs first made programming more efficient. We did not have to write in assembly or use punch cards. We could write DOS and eventually use graphical user interface and even the mouse. I don't know how many of you even remember there was a time before the mouse. And only then we could talk about what Bill Gates said, a computer on every desk and in every home. I still have fond memories of my first PC. It was an Apple IIe. That was my first step into an amazing journey in tech. I probably would not be standing here in this spot if not for that first PC experience. The next major pivot point was the internet itself. With things like Alta Vista and Yahoo, ICQ and MSN Messenger, and later on Google with search and YouTube, the internet made a whole host of things in our world more efficient and easier. We moved from mail to email, to online shopping and e-commerce, and above all, it made an infinite amount of information available at your fingertips. It created a new generation of businesses and services that simply could not have existed without the internet. Think about Amazon and Netflix. And then comes the cloud. How huge that was. Initially, it was about, if you were too small to run your data center, maybe you tried this thing. I still remember hearing a CEO of a Fortune 500 company call this out as a minor fad in 2013. And then in 2017, there were reports that cloud workloads represent over 75% of the industry. As someone that was deep in startup arena during these years, I really experienced this firsthand. My first venture was pre-cloud, and we really sweat through many IT problems before we could actually get to solve our key problems. The second startup was after the introduction of the cloud, and was a dramatically different experience. The cloud almost eliminated these IT problems overnight. And these revolutions didn't just enable smarter, smaller startups. It enabled much bigger companies to go through major revolutions. Think about massive players like Netflix. One pattern that emerges across these inflection points is that each of them brought major change to the industry as well as to our lives in many ways. And it's also visible that we're seeing that the pace of acceleration growing, and the events are coming closer and closer in time. Obviously, the next milestone in this journey was the proliferation of AI and ML. And this meets us in Data at Scale 2022, where data in the lens of AI ML comprised the major part of the event. My colleague Aparna was on this stage back then and introduced the key points we see in the data infrastructure world as we take the impact of the AI revolution. I thought I'll take a few minutes to recap on what has happened since in each of these dimensions. In 2022, Aparna called out these 5 points, and since then we have seen major evolutions. We have seen more applications of AI being trained at a much larger scale. Across the industry, it is now common to see recommendation systems trained on thousands of GPUs, leveraging distributed training to allow better experiences to their users. In the world of ranking and recommendation, a key trend over the last 2 years has been longer user sequences. The tech now allows us to take into account many more past events, and as a result, provide a much better experience. But as we are building long user sequence of thousands and tens of thousands of user interactions, we need to deal with more features, models, and we need to evolve our infrastructure to handle those, and as well as the difference between analytics data and training data. We evaluated file format requirements and designed a new file format called Nimble that provides encoding flexibility and better controls for workloads optimization, optimizing for compression, read and write costs, and allows us to optimize our workloads. We have also introduced Velox into our data infra ecosystems. Simply put, Velox is a high-performance native data processing engine. One of its key features is the ability to process data in vectors rather than individual records. Velox, like Nimble, was developed by Meta to address the extreme data scale needs of growing AI applications and was introduced to open source community so that we can all keep pushing the industry forward together. And why take my word on this? What says demand has outgrown supply more than the NVIDIA stock graph over the last 3 years? And it is not only software. We are seeing more companies working on their own hardware to help relieve supply shortage and allow better optimization and performance and scale. And on that front, Meta recently announced its first AI accelerator, the MTIA V1. I'm inspired by how far we've come in such a short time since Aparna's keynote in 2022, and proud of everyone's efforts to innovate on data demand, optimization, infra, freshness, and observability for broader AI efforts. And while we are still working hard to evolve our data infra to allow the AI revolution to happen, and in many ways we are still early in the journey, we now see that it pales in comparison to the challenges being introduced with the GenAI revolution. As someone that works on these challenges every day, I thought it might be helpful to share my view of what drives success in the GenAI space. And I will frame these under 4 buckets. First, obviously, is the model, where research is evolving at extreme speed. Since the launch of GPT-3 in November 2022, it has barely been a year and a half, and we have seen the tech evolve in ways that normally would have taken many years. GPT moving from 3 to 3.5 to 4, Llama 2 to Llama 3, Bard to Gemini, and these are just a few examples. Second comes compute. To build foundational models, companies need jobs running GPU clusters much larger than we have ever imagined, moving from thousands to tens of thousands of GPUs and even larger clusters has been key in this innovation race, to the point that Meta recently announced it will be running 600,000 GPUs by end of the year. The other 2 are straight in our backyard. The data space is key to making GenAI models work in both the scale of data it feeds as well as the quality of the data. In many ways, data is the secret sauce of foundational models. As we progressed from Llama 1 to Llama 2 to Llama 3, a major part of the process was driven by adding more data of higher quality and higher diversity. This enabled higher performance models, and each generation of models added 10x investment in both the quantity and the quality of data. Let's go deeper into the challenges data for GenAI needs to tackle. First is scale. To allow models to train on data at this massive scale, we need new ways of collecting and storing data. We need ways of handling different modality types. Processing massive amounts of text is very different than massive amounts of high-quality videos. And then there's a long list of questions that frame our journey, starting with what would seem basic. How do we catalog all the different data sets that build this massive corpus of training? How do we make sure every piece of data gets properly reviewed for privacy, security, and integrity policies? How do we balance this extreme scale of data with the desire to allow researchers to be super nimble and quick to experiment, as well as fail fast? How do we allow them to visualize data sets with trillions of tokens? How do we help hundreds of engineers collaborate in order to create a technological feat, such as releasing an industry-leading LLM? And then come the inference challenges. When we think of those, we can talk about fault tolerance. What do we do when a multi-month job fails? Obviously, checkpointing helps, but it also opens up a ton of other challenges. And what about co-location? Keeping data and compute, in this case GPUs, close to each other so we don't melt the network. And trust me, it is not a pretty sight when you get close to melting your network, and then you need to redesign things almost on the spot. So be proactive about it. Think of data placement considerations that take into account the data center capacity to ensure training efficiency, avoid GPU starvation, maintain GPU load balancing. And these questions lead to much more interesting discussions, all the way to how you design your data centers going forward. These are massive changes, but even with these, it's not going to be enough as we think about the future. And this is what really intrigues me. As we move to the next versions of Llama, and knowing that as you extend into more bizarre sources of data, you are likely to get less quality tokens. I wonder, is there even enough high-quality tokens on the web? At what point do we switch to new sources of training data, like synthetic data? When we think about data, we should also be thinking about the quality and diversity. And it's not just that LLMs are very prone to garbage in, garbage out, but we feel data quality is a real differentiator in this game. For one of the key differences, we think we got massive wins in Llama 2 and then in Llama 3 by introducing much smaller scale models of much higher quality data. And we could compete with larger models that did not put same emphasis on data quality. Examples of data quality dimensions we care about include picking data sources with high concentration of knowledge and removing gibberish from the content fed into the training data to maximize learning per token and minimize level of noise. We believe in removing duplication of data to avoid memorization and making training more efficient. And in general, giving high priority to higher quality and validated information sources has proven to be an efficient way for us to go about training. When we think about diversity, we think about building models for the whole world. This means supporting diversity of language, diversity of modalities, be it web documents, research papers, various kinds of media, and diversity of knowledge domains. All of these need to be reflected in the data being fed into the model. It's only with massive diversity we'll be able to solve a large range of problems, from retrieving facts to generating poems and videos, to doing product research and allowing to buy something, and solving hard math. And then comes responsibility and safety. We want data that is helpful, harmless, and honest, i.e. factual. We first need to ask ourselves, how do we make sure the data sets we train on isn't biased or harmful? We need to make sure data is not doing harm, i.e. not toxic, safe for work, and avoid other integrity risks. And we need to make sure that the data is fair, not biased towards age groups, genders, as we are proactively developing technologies to address all of these risks. We also expect regulators to help the whole industry maintain a high bar on these dimensions. Training data for pre-training and fine-tuning heavily depends on scale, quality, and diversity. And due to these traits and others, it would take a lot of time to train models at this scale. So by the time the model is shipped, some of the data it was trained on is already outdated. We also know a model can't answer questions it was not trained on, and that there are specific use cases that depend heavily on the freshness of the data, such as news or results of a recent sports game. And there's even a more extreme use case when we want to deal with events in the future, such as getting the agent to find tickets to a hot show where tickets have not been released yet. The outcome is that models cannot rely solely on their training data in order to respond to events in real time. We need to get the model to understand how to go about acquiring the needed information, even if that information did not exist in training time. The industry is doing this through a combination of tools, as well as leveraging the inference time context window. On one hand, we see more and more tools that models can leverage and get to validate the information they need in order to respond. And on the other hand, there is an ever-growing context window into which we can bring relevant data so that the model can properly answer different use cases. In closing, we talked about where data infra plays in GenAI, and I want to recap the 3 top points. Multimodal datasets require unprecedented scale. In this we are seeing data scale that pushes our systems to extreme, challenging many of our past assumptions and bringing interesting problems into light. Then comes quality and diversity, which are key for creating leading models faster and at lower cost, allowing players to leap ahead in the innovation race. And we are seeing that data at training time has limitations. These can only be addressed by models that, at inference time, know how to go about getting the data they need. They do this through tools as well as utilizing more of the inference context window. And now, if we go back to the series of industry inflection points, the next technology that could pop up is artificial general intelligence, or AGI. To be frank, we don't know if and when AGI will happen. We could easily go into another AI winter before we see AGI coming, or we may never see it at all. But at the current pace of innovation, this could also be just around the corner. I will leave it to you to guess. And to conclude my time with you, I want a quick reminder of why we do at-scale events. These are meant to allow us all to come together as an industry and a community. And this is a core part of the Meta DNA. We see open source as key to progress. In this talk, we touched on Llama, Velox, and Nimble. All of these are now available to the open source community, with the hope that together we bring the industry a major step forward, which no single company could do on its own. Thank you, everyone.
Thank you, Barak. This is really interesting, like just how much this field changed even over the last few short years. What stood out for me is scale, unprecedented scale that's pushing the boundaries of infra. How about you?
For me, it was about the quality and the diversity of data that makes the whole difference. And as Barak talked about, freshness is no longer optional. It is actually making the difference for the most demanding use cases, as we heard. With that, I would love for us to hear from DJ and Daniel about the challenges that generative AI is posing for humanity and how we go about them. DJ is the former chief data scientist at the White House and also a very successful entrepreneur. Daniel is a colleague of mine, director of product management in infra, working on AI, developer, and data infra efforts. Let's hear from them.
DJ, thrilled to be here with you today to kick off Data at Scale.
Thank you.
It's really exciting to be able to talk about these important topics with you today. We've worked together on two different tours, really foundational tours to my career, and you've done some great things in both those tours at LinkedIn and Relate IQ. Mm-hmm. And we've sort of learned a lot of lessons along the way. And today's going to be a conversation about a lot of those lessons we've learned, both in those tours and working in the space. Mm-hmm. DJ, you need no introduction in this space. You've been foundational to so many of the problems within the data space, including the initial formation of data science as a field. Having been chief scientist and chief security officer at LinkedIn, role as VP of product at Relate IQ, CTO at Devoted Health, and of course, let's not forget first chief data scientist under Barack Obama at the White House. So definitely played a foundational role, both in terms of how data science is approached as a field, as well as many of the technologies such as Kafka that we all rely on today. As we proceed through the conversation today, we're going to talk about both not only what we build, but we're going to zoom out in the conversation today to really focus on how we as technologists should think about what we build can be good for society, how we should focus around the teams we build, how we can take on the problems that actually push all of us collectively forward. With that, I did want to dive into a little bit around what we should build. And I want to kick it off with a question around what you think some of these foundational things we should be thinking about as data infrastructure, data science folks look like. What are some of these big challenges we should tackle?
Yeah, well, thanks for having me here, and thanks for everybody joining in. I should also say thank you for that introduction, but what people don't always know is how instrumental you were, Daniel, to making all those things happen. So those technologies would not exist without you, and certainly my life would not have been as fun building those technologies without your help. So I appreciate all of it.
Thank you.
You know, where to start on what do we build and how the space is kind of evolving. You know, on one dimension, our lives still suck. We're still spending a ton of time cleaning data. We're still moving data around, writing too much SQL. Like, there's a bunch of pieces that are still the bare bones. Like, we need to get that better. The other side, there are so many exciting things that are taking place. We have this unbelievable amount of new technology infrastructure that's coming in to support large language models, generative AI, computer vision, all of these ecosystems. And then on the other side of this, we have this wide array of technologies that are out there. And so much so that in some ways, it's hard to choose what technology, it's hard to pick which ones you want and how do you stitch them all together to make this work. But if I had to say it, you know, if you look at society, the number of people who are trying to graduate with degrees in data engineering, data science, want to work on AI, this is one of the most exciting times to be in the space of data, AI, and that broader landscape of things.
Great. Now, these are all exciting things. Let's talk about some of the things you worry about getting attention lost on them as we shift this Gen AI moment. There are some of these, to your point, foundational problems. What are some of the things folks in this room should still be really focused on, shouldn't lose their eye off of as we move to this new moment?
Yeah. So the first one, I think, which we've seen is, and I think it's very easy for us to collectively gloss over the whole world of just basic data hygiene. You know, there's like in the framing of Maslow's hierarchy, one that we use very heavily at LinkedIn was there's food, clothing, water, shelter at the foundation, the bottom of the pyramid. And when you think about that bottom of the pyramid, what is essential? really is clean data, organized data, ability to do good work with that data. If you don't have that, when people just sort of slap on the AI products on top of that, whether it's generative AI, it could be computer vision, could be other type things, we're finding that the limits of what we can do, we hit that ceiling pretty quickly. And so the big limiter oftentimes is high quality data. And the organizations that are making some of the best progress on using AI technologies are the ones with good data shops. It's also important to emphasize everyone is focused on generative AI, but there's so much happening in computer vision. Many of the basic statistical techniques still have incredible relevance. And so it's the Gen AI often can feel like that's the solution we should grab, but there's plenty of other ideas out there that gives just as good results.
Yeah, sounds good. And this is one area where we're going to come back to it, but this is where the data folks in the room really have a role to play in Gen AI. With the industry moving forward so quickly, would love to circle back later and talk to you a little bit about how the data folks can sort of act as that guiding force to make sure the data is being used the right way to both make the Gen AI better, but to make sure we're doing right by society.
Absolutely.
Do that for sure. I do want to shift gears now to how we should be thinking about this from a societal perspective. No doubt Gen AI and what we're building is having and will continue to have a huge impact on the world at large, at people well beyond the tech industry. And so we need to be very thoughtful in how we proceed. Now you've been a big proponent of the multidisciplinary approach when it comes to building these technologies and when it comes to having all the voices in the room. I'd love for you to really dive into that for us a little bit and talk through how we as the data practitioners, as we as the builders should think about bringing these other folks into the fold and make sure we're bringing those perspectives to bear.
Yeah, it's just such an important topic, Daniel. It's like, and for everyone in the audience, this is one of the ones to really emphasize that we get right. What we often forget about, and we think about consequences of what is taking place and what is actually going on. One of the key things that we need to remember is we wield unbelievable power. You know, that classic Spider-Man version analogy of it is, with great power comes great responsibility. We all collectively own that responsibility. What we do with that data, where it goes, all of this is within our scope. And so the basic version, when we looked at this, and we actually did a process when I was just leaving the White House, where we tried to think, should there be an oath for data scientists, just like there's a Hippocratic oath for physicians? And what we came down to at the end of the day is there's actually just a golden rule for data first and foremost, and it's like, treat the data like it was your own loved one's data. Are you treating this data like it was your own kid's data? Are you keeping it secure? Are you keeping it protected? Are you doing all the hygiene things knowing that it's one of your loved ones' data? And very often we skip over that. The second thing I think as we think about these things is how we have to also remember privacy, security go hand in hand. A lot of times we're not thinking about all these other aspects. And then one of the other ones that I would just emphasize, and the reason it's so important to have a diverse educational background, you're learning every day, is you have to be in tune with the societal issues. You have to be really thinking about what's there. And I'll give you a very concrete analogy. So when I was US Chief Data Scientist, and I was thrown into a bunch of problems, there's a perspective that I brought to the table from my life experiences, from the people who've educated me, the people I know, people like you, all the problems we worked on. And I didn't fully appreciate until I had been I had the ability to really sit with other people to understand the implications of how their data was being treated, what the ramifications would be. It would be very specific. So for example, when we're working on thinking about data around rare diseases, there's a population of people who are saying, you know what, I don't care, just use my data everywhere. And oftentimes you see them posting in very public forums, like on Facebook groups, other type things. Okay, great. They see no other avenue to do that. That's totally reasonable. There's another population who are like saying, hey, in the past, and particularly here in the United States, we've had egregious violations of trust. Henrietta Lacks, for example, and her data being used without any compensation, any process, all of those things. So how do we get this right?
Yep.
If you're going to get it right, there's a couple lessons I've learned. Number one, you can't do this just from some back office, sort of saying, oh, the customer's out there, or just doing some kind of persona approach. You just can't have personas are like going to the photo store and you see all these frames of people who look like amazing, and you're just like, who are these people? Like, no family looks like this.
Yep.
There's a kid not
It's
sticking
an
his tongue out.
idealized representation.
Yeah,
That's it.
It's idealized.
Yep.
You need you need that, like the real people at the table, not some survey. You need to be talking to them. That is the thing. And the way we say it is the data points have names. They're not just data points. They have names. You need to learn their names. You need to learn their stories. And then you need to be able to communicate and tell others about their stories. Once you're able to do that, then you are now a responsible steward of that data. But until you can do that, you're really just a data scientist in a back office. And we have so much more to offer than just being relegated to that back office kind of role.
That makes sense, yes. Now once we keep all that in mind and we're being respectful of people's data, we view it at the data as the person, there's the person behind that data point. There's a big aspect to this around problem selection, and are we investing in the right areas? Now, of course, you were doing a lot of that as the US chief data scientist. That was the mandate, to make sure people's data was being used for their benefit. As those of us in the tech industry, how would you recommend we select problems? Like, how would you recommend we make sure we're not just doing the things that look good on the benchmark tests, but the things that are actually doing good in the world?
Yeah. Well, the first portion of it is actually the mission statement of the U.S. Chief Data Scientist is to responsibly unleash the power of data to benefit all Americans. And so the two components of this are, both to do it in a responsible way, to make sure we're doing it, but also to make sure that we are doing this to benefit everyone. And so it has a very clear mandate to also make sure that we are using America's data to benefit and unlock it for innovation purposes, security purposes, all of that that's in there. So how do we think about our problems? I think one thing that's out there is we've seen the true raw power of data scientists in times that we often forget. Let's take just most recently the COVID crisis. During COVID, who were the people who really showed up first? And a bunch of this is in Michael Lewis's book, Premonition. Obviously, we were one of the teams that showed up to take care of the California COVID response for the first bit, setting up the testing centers, all these different things. But you had all these other groups building models, like the COVID tracking project was the core source of data for the United States. You had versions of this around the world. And so you had this new form of first responder, which is a data scientist. And so you could work on problems like that. You could build out problems around like crisis text line, which is the backbone of 988, which is the national suicide hotline. Things like that, to use data in effective ways to help people. There's healthcare systems. There's all sorts of ways to do it. The way I would think about this is, are you, that classic adage, are you using your time? Are you working on the most important thing that you could at that moment in time? Now, that could be aligned with the company goals or other type things. But the key thing that you're having to choose is this maximal in the impact? And the impact is not one-dimensional across some OKR, objective key results, key performance indicator. Yep. We often like to think, my job is to move X to Y. Your job is to not only think about X to Y, but to think about all the implications of what happens if we move it from X to Y, and all the second order impacts, the third order impacts, as well as, is this the right metric? Is this a holistic right thing? Because sometimes, and we saw this at LinkedIn acutely, was you could crank up a dial and get virality, but then you were going to kill the network's effectivity, the ability for that network to be useful for people over time. So we had to be very smart and as a good steward of these things. For those that are gardeners, you can put a ton of fertilizer on the food. Doesn't mean it's going to work. It's a really great idea over time.
Yeah, makes sense. So that's great thinking in our day job as we go about approaching these problems. One other thing I do want to touch on before we move on to culture is around how we can use the valuable skills we all have in this room to benefit the government, our communities around us, society at large. And you've been a big proponent of public service. I think when a lot of people think public service, they think full-time roles. You laid out a lot of where we should go in the US national AI strategy. How should we think about that? How can we give back in a way that potentially works well with our current responsibilities?
Mm-hmm. Well, one of the benefits that we have being working on these type of technologies is we are literally building the next future of what services and products can take place. And so I am a huge proponent of doing public service, because my mentor, Ash Carter, late Secretary of Defense, used to say, is like, once you've had a taste of it, you can't go back. You always have to find some way to help. There's always something to do. Now, do you have to go in all full time always? No. There's tons of things locally in your city, your neighborhood. You can ask, like, hey, could we improve a local service? I'll be very concrete. Like here in the SF Bay Area, there's a program around foster kids and trying to figure out how we can improve making sure they're getting connected with the right families. They're doing all the, they're getting the services they need. There's a ton of data infrastructure analytics there. There's a service called the U.S. Digital Response that was created in the early days of COVID to help the local counties give services. How often do we get to complain as technologists that we're like, this part of my city sucks, this part of my government sucks? Well, if you're complaining about it, what the hell are you doing about it? You're a technologist, you got all these skills, you got these degrees, and you can't make your town or city better? Then what's as good as your skills? Bring your A game to make better for not only your town, your county, but you can do it around the world. You can volunteer on a program somewhere else around the world to help them out. And the hardest thing is just finding a place where, hey, I can apply my skills, using skills, and do these things. And there's a few areas. You can do it through U.S. Digital Response. You can do it through Code for America. There's a whole ton of others. And there's oftentimes fellowship programs or other things where you take a year off, President to Innovation Fellows, other type of things where you go into public service for a year. Could be at the state level, could be at the federal level, could be at the international level. But there are so many places you can take your skills and have an impact. So we're talking about this from the Meta Facebook landscape. We often think of the billions of things. You can literally have an impact on someone's lives at a billions of scale when you work on government. You work on the U.S. federal government, you're impacting a couple 100 million people right off the bat because it's the U.S., plus all around the world is because everyone looks to the U.S. at how to do things. You can have massive phenomenal impact as a result.
Yeah, and I think I remember you saying that you were talking about problems that hit the trillions when you were in that White House role. Those are problems even by our scale are just enormous and can have huge impact.
So our framing when we worked on it was it's got to impact half of the United States population, 50% of the population, impact $1 trillion of U.S. spend, or help a population that has no recourse. So what are problems like that? Healthcare, criminal justice reform, the climate. It's not going to impact half the population. It's going to impact the whole world. And you can go on and on and on about these things. Education, so many more other things. So tackling those problems are phenomenal. And now I think something to emphasize to everybody out there is we often think of like, oh, how am I supposed to do it from my company perspective? But a quick story from LinkedIn time that we got to work together. People don't realize a job matching engine of LinkedIn was designed initially because I had all these friends who were coming back from the conflicts in Iraq and Afghanistan, were leaving military service and couldn't get the jobs that they should get. And so we figured if we can build a job engine and algorithm to support them, it's going to work for everybody else. And so because we were the technologists who owned that system, owned that tech, we got to actually build something that worked for a population that was really suffering, as well as for this much broader use case, and raised a ton of money also for the company in terms of revenue.
Yep, absolutely. Do good, and you also do well by the business when you do that.
That's right.
Sure. Let's turn a little bit to the culture and sort of the team you have to build, because none of this happens without that team being in place. So One of the things you often talk about the data scientist playing a role as is the Spock on the bridge, Spock being in reference to Spock in Star Trek. How, in this new Gen AI moment, can we make sure that we're as effective Spocks on the bridge to make sure Gen AI is steered in the right direction?
So the first thing I think is engineers, we love to complain. As data scientists, technologists, we love to complain. We're not in the room. We're not in there. Why aren't we in the room? Like, what prevents us from being in the room? And one of the most powerful things, this dates back to the early days of Facebook, when Jeff Hammerbacher and myself were kind of trying to figure out what job titles to call our teams, and we finally landed on this term data scientist. The thing I think which we saw, which was really powerful, is the job took off because people really didn't know what it meant. But honestly, it allowed people to be in the room, and people are like, oh, you're smart, you're adding value, you have context. And when you have context, you can actually be helpful. And so the first thing is to figure out, how do you get a seat at the table? And oftentimes we're like, well, let's just let the product manager take this, or the project manager, or somebody else. No, you say the product manager and the technologists need to come to this meeting. They need to be in that room. They need to have the context, because if you don't have the context, you can't actually solve the problem. The second thing is, when you're in that room, have you done all the prep? Have you done all the work to really represent things? Do you know the metrics? Do you understand the business? Very times we're like, we're not going to do the hard work to understand the business. And then we complain people don't understand the technology. Well, those people are also complaining we don't understand their world. Yep. So you've got to get out of your comfort zone and understand the broader thing. And then once you're in there, you have to figure out how you're going to solve the problem. How are you adding value and doing it? And like, people kind of push back on this every time. I tell them, look, if I'm in a meeting with the president, my job is to find a way to add value. And that isn't just by like speaking up. It's not like you just get room to speak up. You have to add value in those conversations. There's not very much time. The problems are so intense. You have to figure it out. And what I'm doing is I'm trying to solve a problem, but I have an extra angle on this. My angle of attack is I get to bring data to the fight, and I get to use that to try to add value. And so you have to get to the table. You have to earn your keep your place at the table, and then keep moving up by adding value with the technology and the skills that you bring.
Yeah, and so really it is that understanding the overall, the higher level problems we're trying to solve.
That's right.
And always aiming for that. Understanding you have a superpower to add to that, but that superpower should layer up to the bigger thing as well. And don't lose sight of that bigger thing you're going after.
And this would be one of the key things is it's one of the most painful things, and I think a thing that is missing in our educational system is this component of the liberal arts. We don't have people who know how to storytell. We don't have theater. We don't have people who are taking literature or all these other things. You can still do this. It's not too late. Take improv. Do these other classes. That ability to communicate, to create human connection, that's what's needed. If I go into a room with very intense situation, and I pull up a chart and I say, as you can see, that's dead on arrival. Like, if everyone's like, what do you see? Like, that's my pet peeve word, is people are like, as you can see in this chart. It's like, no one can see it. You haven't told me. Tell a story, tell a narrative. You may use data to back you up, but figure out how to actually tell a story. And the way to do that is that you find the people that actually are the data points, have their story, bring that story back into the room, and then scale that with data.
Makes sense. Before we close out, we have a big group of data infrastructure professionals here. We have the community gathered in this room today. One of the big strengths in the early days of the data field, data science, back in our LinkedIn era, it's a community we're both part of and we've benefited tremendously from. We have friendships to this day, was that early on we came together across companies. We were solving problems that were much bigger and much more difficult to solve than any one company could get their arms around. And that community aspect of just getting together and solving really hard problems and commiserating together was very helpful in the early days of the data infrastructure industry, data science.
Essential.
Overall. Essential.
Couldn't have happened without them.
Absolutely. Now with GenAI today, there is a feeling that this is sort of like our race and everyone needs to win. And I do have some worry that that community is not, that same type of community isn't going to take hold. Mm-hmm. I'd love your take on this.
Yeah. I mean, the first version that we think we found, and this was true in the early days of Facebook, LinkedIn, others, is we just got together to chat. Like we would just get the teams together and just share pizza, Chinese food, you name it. We just get together and trade notes about what's working, what's not. In the AI space, it has been very much a flat out run, but actually far more collaboration is happening, but people don't realize it. I think we need to make it okay to share. We need to find ways to do it. We need to have the conferences, the events, the other type of places where we normalize sharing what works, what doesn't. Why is this so important? It's because this game is so much bigger than just creating an LLM. We have the potential of AGI on the horizon in our lifetime. What is that going to mean? What are those things? We have such big problems. We are going to see climate change causing massive challenges across the world. We're going to have massive migration. We have serious conflicts that are taking place, like we've seen in these gray zone areas, like we're seeing in Ukraine, we're seeing in the Middle East, we're seeing in other places in Latin America. These are the challenges of today. And so how are we going to be thinking about using these technologies? And how are we going to be able to realize when we have the next pandemic or another issue that we can come together to bring our skills to solve the problems of humanity? That may sound highfalutin, but we just saw it happen. Yep. And we saw people rise to the occasion and technology and everyone sort of shifting gears to help on that front. We need ourselves to realize that there's corporations and there are big entities. I get it. There's job, there's money on the line, but there's something more important. There's relationships, there's people. We are a community. You are more than your company is. You are more than just your job title. We are a community, and we work best when we think about data science, AI. These are team sports. And when we do that, that's when we collectively win. Because fundamentally, at the end of the day, what we are going for is to not just win for today. We are here to win for our kids and our kids' kids. And that is on a global scale.
Amazing words to leave us with, DJ. DJ, it's been so much fun joining you here today in conversation at your house on these topics we care so much about. For everyone at Data at Scale, I really hope you take this message forward. You really take forward that we have a big responsibility to play in building the right things, in using people's data responsibly, and understanding that there is a person behind what we're doing. And you bring that community aspect forward so we solve these hard problems together. Thank you.
Thanks, Daniel. That was so fun, as always.
Thank you, DJ and Daniel, for this inspiring session. Elena, what stood out for me in this session was the importance of data hygiene to get the most out of the models. And even more importantly, as DJ shared from his experience in the White House, the responsible use of AI that is going to make a difference in a positive way for humanity. How about yourself?
For me, the big part is around taking a community approach to tackling these challenges and solving for the good of all. Community has been a big part of AI evolution. And to talk to us about evolution of data management systems at Meta, we'll hear next from Pedro and Amit. Pedro has been with Meta for 11 years. He worked on a large number of systems and projects, and has contributed to open source actively. Amit is engineering director of compute engines at Meta, and together they will talk about how we're evolving our monolithic data management infrastructure to more composable one and reaping the benefits in the process. Let's hear from them.
Hello, everyone. Welcome to our Data at Scale session on composable data management. I'm Amit Purohit, and I will co-present the session with Pedro on how we are evolving our data stack for future needs. The data industry has changed significantly in the last 50 years. Data stores were invented in 1960s But 70s is when we saw transaction systems emerging. This change has evolved for many reasons, but the biggest one is that our customer needs have evolved continuously. As the needs evolve, engineering teams around the world build systems to address them. Years ago, online transaction systems were a critical thing. But in order to extract the data out of those transaction systems, we built analytics use cases. And then to access the data faster, the need increased to become real-time analytics and streaming. The latest to this addition is GenAI. This means that data infrastructure has to evolve continuously to support the innovation and changing requirements. This slide has an example of existing workloads. They were different 5 years ago. They are definitely different from that, and they're different. They will be different in 5 years from today. The speed of innovation has definitely helped our customers, but also created these verticals and in turn giant monoliths, which is the root cause of our fragmentation challenge. As engineers, this required a lot of plumbing, as data moved between these systems and we need to spend time and money to engineer that plumbing. This all meant that we were continuously rebuilding rather than reusing. Now, I'm not saying that in order to solve this problem, we just converge. Convergence is hard, complex, costly, and is not the only solution. We're basically trying to plain and simple, efficiently run these systems at scale and continue to innovate. Now, this is not just a problem for our industry. Auto industry went through a similar transformation in the last few decades, where they leveraged sharing and reusing every part of the car, starting from windows, mirrors, seats, batteries, braking systems. So it is doable, but saying this in a presentation is much easier than actually doing it. So what have we discussed so far? Customer needs have evolved rapidly and continuously. This has created these verticals, but also monoliths with little or no reusability. This fragmentation increases cost. On one hand, the increased engineering cost. Look at SQL dialects being incompatible between engines. So people have to do a lot of juggles to move their workloads. And engineers are doing a bunch of work in plumbing rather than innovating. And that's not all. This leads to compute costs for businesses going high, super high. We are talking about millions and millions of dollars in every company every year. That can't be efficient for anyone. All this felt like early 90s for big data systems. And that's what triggered us a few years ago to see if there's a better way to do all this. Well, there is. So the way this generally works in our team is that I create all the problems and then Pedro comes in and fixes them. So Pedro will cover what we've been doing at Meta to address the problem of fragmentation and improve efficiency for compute infrastructure. Over to Pedro.
All right. Thank you, Amit. I'm Pedro. I'm a software engineer at the compute team at Meta. And I'm here to talk a little bit more about the approach we took to make sure we could continue scaling our data organization while getting resource savings in return. So in this talk, I'm going to talk a little bit more about the concept of composability in data management. Then I'll describe one of the main projects we have on the space called Velox, and I'll hand over to Amit for discussing next steps. So the idea of composability in data management started with the Shared Foundation project, which was something we started about 4 years ago inside Meta. So the ideas of Shared Foundation was threefold. First of all, we had too many systems focused on different workloads. So the idea was to, as much as we can, consolidate them into fewer systems that are just more manageable from the organizational side. Of course, we knew that we couldn't consolidate all those systems for the places where we actually needed specialized systems. The idea was to build reusable components that could be shared across those systems. And as much as we could, we tried to build those systems and those APIs based on open standards. So this program eventually evolved into what we call the Composable Data Management System today, where the idea is that data management systems in the industry should be developed less vertically and more horizontally. Right? So with this idea that we should build more APIs, more libraries, and more components that can be reused across those systems, so we developed fewer of them. So of course, the idea is that if we develop fewer components, we can spend a lot more time optimizing them, so usually get efficiency gains. But also the idea is that with fewer components, we need to invest into fewer projects so we can develop a few components and share them across different silos so we improve our engineering efficiency. But also the idea is that if we have fewer components, we can also provide a more consistent user experience for our users. So for further reading, The initial idea about shared foundations was published at CIDR in 2023. And this new vision of composable data management systems was published at BLDB in 2024. In this paper, we made the observation that even though those systems are specialized and vertically integrated, if you really look at what they're doing inside, they're usually very similar. So they're all composed of the same logical layers. So each one of those systems has some sort of language layer that is able to take some input SQL query or a data frame program or some kind of DSL, parse that and translate that into an intermediate representation. All those systems have some sort of optimizer that can take this internal representation and generate another one that is more efficient for execution. All of them have some sort of execution library that is able to execute this internal representation, given the resources given by the execution runtime environment. We also made the observation that this model is pretty general. So you can look at every single data management system in the industry, and all of them are composed of the same set of layers. In some systems, some of those layers might be a little more developed. Some of them, they might be a little less sophisticated, but all of them are composed of the same layers. And not just that, so this model is not just general, but they're predominantly the same. So if you look at SQL parsers between transactional and analytic systems, like they might not be exactly the same, but they're by far mostly the same. Same thing for execution engines. Like they're not exactly the same, but they're very, very similar. So the idea of composable data management systems is that we should focus on the similarities, or we should focus on what those systems do, which are the exact same, rather than just focus on the fact that they have some differences and then just developing everything from scratch, right? So the idea is just trying to unify everything that is similar and provide extensibility APIs so that specialized behavior can be added and can be integrated into the system. So the part is that this is all great, like all those systems are composed of the same layers, but what do we do about this? So there are a few reasons why this is important. So the first one is that those systems are constantly evolving, as Amit said. So in the future, as those systems evolve, if we already have reusable libraries that we can just assemble, like we're going to be able to move much faster in the future. But not just that, even for existing systems, we know that refactoring those systems and making efficiency improvements it's expensive for the organization. Like a lot of engineering costs goes into that. But if we could do that in a more reusable manner, like it would also help us reduce the cost as we make those optimizations, right? So we took a bold step and say, instead of continue optimizing those systems individually, let's actually try to develop that as a reusable component that can be integrated with all the systems. And of course, the idea was that we want to develop fewer components, hopefully just one, and then kind of multiply the returns we get over that. So this is how we got to Velox. And of course, if we're optimizing something, we want to optimize where most of the time is spent, or the place that took most of the resources, which is the execution engine. So Velox is a project we started to address this specific problem. So Velox is a new execution engine that we created about 2022. The idea is to create a new state-of-the-art C++ library that can centralize our investment and multiply it. So we created Velox in 2022. It was open source in 2022. And we've been seeing a really fast community adoption. So up to this day, we see more than 200 individual contributors across the community, and more than 20 companies working with us and collaborating with us in developing Velox. So it's already comprised of a kind of really large open source community. And the vision behind the project is really to commoditize execution in data management. So giving you a little more details about Velox. So Velox is a C++ execution engine developed as a library, and this is different from being a full-blown database management system. So the idea is that Velox doesn't have a language layer. It doesn't have an optimizer. So all Velox does is taking a fully optimized execution plan and executing it locally with the resources you have available in your host. So that's essentially what you do. You take a fully optimized query plan, and then the engines integrating your Velox are responsible for providing a language layer, for providing an optimizer, and for providing the runtime environment. So Velox is fully extensible. It was meant to be reusable, so we developed Velox from scratch with this idea of coming up with the right APIs that can be reused across those systems. We like to say that Velox is engine agnostic, so you can reuse Velox in many different engines, but it's also dialect agnostic. So you can extend Velox in multiple ways to follow different semantics from different SQL dialects. So you can add different data types to Velox, you can add new function, scalar function, aggregate functions, you can add new operators. So the library is fully extensible. You can tweak them to follow the specific behavior you're looking for. So Velox in itself is also modular. So the Velox the library has many different components. At the core of everything, there's a columnar layout component, which is compatible with Apache Arrow. There's an expression evaluation component that lets you execute expressions on top of this columnar layout data. There are SQL operators, and there's many more. So Velox is currently integrated with many systems inside Meta. The two main integrations are one, Prestissimo, which is the idea of integrating Velox inside Presto. And then the community also created the project Gluten, which provides a way to run Velox query plans inside Spark. So for those two systems, they provide the exact same user experience. So you can still express your queries using Presto SQL and Spark SQL. You just notice that your queries will run faster. So those are the two main integrations, but inside Meta, we also use Velox in many other different contexts. So we use Velox in feature engineering. We use Velox in many places in the real-time data infrastructure, in database ingestion, data warehouse ingestion, and even in the log process, on the log messaging pipe. We also have a new time series database developed based on Velox, and there are many more integrations. These are just a couple of examples of how Velox is helping us improve the cost and making more efficiency gains in our internal workloads. So on the left side, it shows some results for Prestissimo. So it shows a comparison between the original Presto Java stack versus Prestissimo, which is the Presto version running on top of Velox, and it shows the average speed up we're seeing from production queries. So those are actually production workloads. So we usually see about 3x performance gains as we move things from the Java stack to C++. On the right side, there's some numbers provided by our partners from Intel. So it shows numbers from both TPC-H and TPC-DS, and shows about kind of the same level of performance gains. Like you can see that we also gained 3x in some of those synthetic benchmark results. To get all those performance efficiency gains, we really leverage on three main data processing techniques. The first of them is just vectorization, which is this idea of decomposing larger computations into smaller and really concise loops that can be more efficiently executed in modern hardware. So the idea is just trying to minimize CPU stalls and trying to provide a really nice and more memory-friendly access pattern. Second one is compressed execution. So Velox is based on columnar layout, and all of those layouts provide different ways to encode the data, like dictionaries, constants, RLE, frame of references, and whatnot. So the idea is that we can actually leverage the data encodings to provide a more efficient execution path. Not just that, but even as you execute operators, you can also generate compressed data in many cases. So just playing with this fact that data is encoded, you can generate encoded data, and in many cases, you can provide a more efficient execution. And lastly, this idea of adaptivity, which is usually when executing a query or a query plan, you're doing the exact same computation over many, many batches of data. So you can actually learn from the execution of previous batch to try to optimize the future execution of new batches. So we use that in many different places. You can use that to reorder filters and reorder conjuncts. You use that to kind of guide your prefetching from the remote I/O and many other different places. So in summary, a lot of engineering efforts and investment goes into optimizing our systems. But at least with Velox, with the composable data stack, we can do that in a more reusable and a more composable manner. And with that, I'll hand back to Amit.
All right. Thanks, Pedro, for an in-depth analysis of Velox and how we are evolving our data stack to meet the needs of the future. So we started this talk about how customer needs are evolving rapidly. This created spatialization, but also created monoliths. All this led to data management compute costs rising significantly high over the years. To reduce the cost, we started investing in Velox as a key pillar of our composable data system story and as an execution engine. As Pedro stated, this has already given us 2 to 3x efficiency over many different workloads. So is that it? Well, not really. We want to innovate in other layers in parallel. Parquet has been a de facto standard for a large part of the decade on file formats. But we believe there's significant opportunity to save compute costs and storage costs in future through another file format. We call it Nimble. We recently open sourced Nimble as well. Nimble is more efficient for training tables, and we believe Nimble is critical for data warehouses of future. Why do we say so? Well, because it's fast, extensible, and efficient. Fast, because it can leverage parallel hardware. Extensible because it decouples stream encoding from the underlying physical layout of the tables. And efficient because it is built for workloads with wide tables, which is generally found in feature engineering and training tables. So we can say that Velox is changing the cost structures already. Everyone wants a 3x cheaper workload, and with Velox, we are consolidating at the software layer. But is that all what we can do? No, we believe there's more innovation possible. In order to reduce the cost to as low as physically possible, we need to get to hardware acceleration. We need to combine software plus hardware, and we believe we can go up to another 10x efficiency for our workloads. 10x on top of already 3x efficient improvement. That could be massive for big data industry. Now, this isn't one of those science fiction things. This is real and in our sight in the next 3 years. But this will require our industry to come together to consolidate at the software layer, which is already happening with Velox and hardware layer. We already see Intel integrating with Gluten, and we see other hardware vendors like Neuroblade integrating Velox natively. So this is happening, but we need to work together as an industry to make this future real and soup. And if we can pull this together, we will enable some of the most critical customer scenarios, including GenAI, in a cost-efficient way and not create more fragmentation. I, for one, am super optimistic about this future, and with Meta, we're excited to contribute towards this future. Thank you all for watching.
Thank you, Pedro and Amit. I really liked how the Velox enables reusability and composability across data services. How about you?
For me, it was inspiring to hear about the 3x efficiency gains this architecture allows. And more than this, the way they talk about hardware acceleration enabling 10x efficiency gains in the future. Quite hard to believe, but that's what the team is aiming at. Pretty inspiring. Next, I'd love for us to hear from Murali. Murali is the CTO and head of engineering for Razorpay. Razorpay is India's largest payment gateway. Murali is going to talk with us about how he and his team are developing the data stack to tackle immense scale. After Murali's session, we're going to have a short break. Let's hear from Murali.
Hello everyone, I'm Murali Brahmadesam, CTO and Head of Engineering at Razorpay, the largest and fastest growing payment gateway in India. Thank you for the opportunity to get into the details of our stack. Let me give a brief overview of my journey so far. I've been a data guy for 2 decades. I spent the first decade of my career at Microsoft. I built various storage systems and data systems and ML platforms. Next, I spent time at Amazon, primarily working on Amazon Aurora database, which I eventually led. From 2022, I am working at Razorpay as the head of engineering and CTO. There are several products that we build, and the primary ones are Payment Gateway. This is our leading product. And we have a neo-banking offering called as Razorpay X that allows businesses to manage their current accounts and so forth. We have a offline payment systems called as Razorpay POS. We have devices that our merchants use for collecting payments. And we have a rewards and engagement platform, which we use to provide offers in checkout experience. Let me explain the Razorpay's mission. Our mission is to become the one-stop money movement platform for businesses. To begin, let me explain a little bit more on what we mean by money movement. In this example, there is a store, which could be an offline store or an online store. The customer purchases goods and services from the store. The store themselves do not build the product. They use a manufacturer to make the product. They use vendors to get services of software, hardware, and other services. They also have employees that serve the needs for the customer. In this case, the customer pays the merchant. The merchant then places order with the manufacturer, gets the goods, places order with vendor for various services, gives the appropriate amount of money for their services. They also pay their employees. Let's look at how this money movement for a business works with Razorpay in the picture. For an offline store, we give a POS device that the customer can use to place the order. For an online store, typically businesses have a website or an app that they can give to the customer to place the order. When the customer places an order in an online setting, when they go through the checkout process, Razorpay code starts running and presents the customer with various payment methods like credit card, debit card, pay through bank, cash on delivery, and so forth. And once the customer pays the business, Razorpay collects the money on behalf of the business from the customer and deposits the money through settlement service on the current account that the business has with a bank. Essentially, Razorpay can allow the business to manage their current account more efficiently. When the business places an order with a manufacturer, they have to send money to the manufacturer and they can use Razorpay payout service. Similarly, when a vendor sends an invoice, Razorpay can manage the invoice and pay the vendor at appropriate time using vendor payment service. The business can also schedule payments for recurring payments. In case of employees, we have a payroll service that the business can use to pay the employee. For day-to-day cash management, the business can use Razorpay's corporate credit card. So imagine you are a startup founder. Instead of giving money to your employee to spend for meals and so forth, you can ask Razorpay to give corporate credit card for your employees. So when the employees spend their money, that can be managed easier. And we also found that a lot of startups spend a lot of time in managing payrolls, where when an employee asks for a cash advance, the founder has to spend quite a bit of time tracking that money and collecting it back or adjusting in the salary. Razorpay solves all of that problem with payroll. Now and then, the business also would like cash advance. For example, because these businesses operate by delivering goods and collecting money later, they might run out of cash at the end of the month to pay their employees, in which case they can ask Razorpay for loans, and we have such service. As you can see, Razorpay helps in money movement for all aspects of a business need. Let's look at Razorpay's growth story. We started in 2014 when we onboarded the first business. Over time, we have added lots of businesses, and as you can see in the diagram, we have now more than 5 million businesses. We also process a lot of money through our system. For example, in 2017, we processed $1 billion through our platform, and we call it total payment volume. Every 2 to 2.5 years, we are doing 10x that growth. For example, in 2019, we processed $10 billion worth of TPV. Now we are processing $150 billion worth of TPV. So we have a very highly scalable payment service. Let's look at a graph which shows the transactions that are processed on the Razorpay platform in a typical week. This graph is showing that there is peaks and valleys and spikes of the transactions that are being processed at the Razorpay payment gateway service. As you can see, the transaction volume never goes to zero. That means that our platform has to be very highly available because commerce never sleeps and our platform never sleeps. Let's go through how we keep our systems up. We have achieved a high availability of 99.99% availability. When you design a service, you have to keep in mind the availability of all the dependencies that you use. If your dependency is of lower availability, then your service will have similar availability. So we spent the last 2 years in improving our availability by first choosing the right database architecture. We chose Aurora database service with multi-AZ deployment availability, which gives 4 nines of availability, which is 99.9% availability. So all our critical data needs are going through Aurora databases. We also found that the surge in connections that might happen are not handled well with the databases. So we implemented proxy servers on top of these databases so that the connection surges are handled in a more graceful manner. We also looked at our existing monolith service that was built in 2014. At that time, we had used PHP as the technology and we had built a monolith. Over time, we have realized that this doesn't scale because the code has to be modified without regressions. We chose Golang as our technology, and we have enabled many microservices to be built. So our monolith has been replaced with microservices. Each service team now has destiny in their hands. Now they can deploy smaller services at their own pace. And because there are so many microservices, the single point of failure has been eliminated. So we are having high availability. Let's look at, once you have high availability, how we protect from attacks. In terms of security, because you are a payment system, we get a lot of attacks. For example, the last year, we successfully mitigated 542 distributed denial of service attacks. How do we do that? This amounts to more than one attack per day. We have written a very detailed blog for which I have given a link in the slide. We started with creating granular rate limiters in our load balancing layer and our firewall layer. We looked at applying limits at a merchant level. Second, we looked at what are the APIs they are calling. So we are able to have a very granular API level limits. We also found that we need to put limits at identifiers such as IP addresses so that we can quickly block the IP addresses that are attacking our service. We also found that many times merchants would be actually doing a sale event, which if we are not recognizing properly, we might be preventing our merchants from using our platform's capability. So we built very granular AI models that builds time series at a merchant level. With this AI model capability, we are able to identify whether a merchant is having a sale event or not. For example, in India, the cricket matches that happen through IPL is a very unique event where just half an hour before the cricket match, we get 10x the load from all these gaming sites. We quickly identify that this is an expected pattern and we allow such traffic through. With both the rate limiters at the load balancer and firewall and the AI models, we are able to handle such diverse patterns that happens for merchants in our system. We didn't stop there. We took these signals and put them in our API layer also, so that the API layer can also throttle such surge in connections, surge in APIs. So we have defense in depth. So we are not just protecting attacks at the surface layer, we're also protecting at the API layer. Now that we have highly available system, now we have to protect against transactional risks also. Here, I'm going to talk about phishing, identity theft. These are the top ones that are quite obvious. I'm going to spend a little bit more time explaining what is a chargeback. When a customer places an order with a merchant, and if they are not asking for a refund from the merchant, but are asking the payment system for money back, it's called as a chargeback. We see a lot of that. We also see that fraudsters somehow steal credit cards and test that credit card with our system. If it is successful, then they would come back to do a lot more frauds. These 4 types of frauds are very prevalent in our system. How do we protect our system and our customers with these frauds? We started with building a very scalable rule engine that looks at each transaction against 400 rules that we have crafted over time. These include velocity checks. For example, what is the frequency of such transaction with a particular payment method? We can identify that. We also understand the typical pattern of transaction at a merchant level. So if we are seeing a lot more transactions, we can potentially flag it as fraudulent transactions. To do all of these things, we had to build risk scoring AI models that takes in 500 different parameters. These are derived parameters. So with the rule engine that looks at 400 rules and AI models that look at 500 plus derived parameters, we're able to with high confidence determine if we should allow a transaction or not. But this is not enough. We had to also give control to our operators for human intervention. So we have built a very good maker-checker tool that our risk specialists would use to determine if to allow or disallow a transaction. With all of these three capabilities, we are able to manage high transaction volume with low risks. I talked about transaction risks, but there are also business risks. How do we protect our businesses that use our platform from these risks? Let me give you an example of a risk. In India, 30% of e-commerce orders suffers from what we call return to origin problem. What is RTO? When a customer places an order, the e-commerce site would send the package from its warehouse to the customer. The customer might just refuse to accept it and send it back to the warehouse. Essentially, 30% of e-commerce orders are being returned back to the origin. Imagine that you are a small business owner running an e-commerce site where you are seeing 30% of your order coming back to your warehouse. You have lost a lot of opportunity and you are spending a lot of money on shipments back and forth from the warehouse. At Razorpay, we have technology to reduce this RTO by 50 to 70%. How do we do that? We first provide configurable payment methods to the merchants. Merchants, when they see the checkout journey of a customer, can provide different payment methods. For example, RTO is very high if you give cash on delivery or payment on delivery option. Instead of that, the merchant can choose to provide credit card or debit card as payment options. And it can at least collect part of the payment so that they can reduce the chance that a customer is going to return it back. But the merchant does not have the insight whether a particular customer is going to return it back. In which case, Razorpay has granular AI model that is built at a merchant level. At a payment gateway level, we see a single customer placing orders across merchants. So we know more about a customer than the merchants themselves because the merchant sees the transaction only within their site. So using our AI models, we can predict whether a customer has high propensity of returning the package back. And we inform the merchant's website in the checkout journey with that probability score that can enable the merchant to provide different payment methods. We are so confident about our AI model that we even pay the cost of shipping the goods back if we were wrong. For example, if we thought that the package would not be returned by the customer, but the customer chose to return it anyways, we take care of the shipping cost. That's how much confident we are with our AI models. With these two capabilities, we also added an experimentation platform that enables merchants to deploy, choose different models and different customer experience in the checkout so that they can trade off between revenue and RTO. Because if you are reducing a lot more offers from going through the checkout journey, then you are potentially having lower revenue. But that is a decision that a business owner can take. So we give all that capability to the business owner so that they can reduce the RTO. I've talked about availability, I've talked about security, I've talked about reliability, all with high scalability. All of these things are possible only when the cost is kept at check. Let me talk about how we run our infrastructure very efficiently. The last 2 years, we have seen incredible growth in the total payment volume that went through our platform. We grew by 70% in terms of the total payment that we processed, but our costs reduced by 60%. This is quite unique. How did we do that? First, we started with giving the control and visibility of the cost to engineers who are developing services. We gave access to the cloud console to the developer so that the developer can know the cost of the services that they are developing. We also took a lot of goals to granularly tag each service developed by each developer so that they can be very aware of the cost of the goods. And we took goals to reduce the cost so that we can run our infrastructure very efficiently. Second, we also inspected every service that we developed and the services that we run ourselves. we found that many of our self-managed services are not cost efficient. So we chose to migrate these services to managed services, which have equivalent capability but run in a very cost efficient manner. And we automated across the stack relentlessly. For example, we all know that running a service in spot instances is much cost efficient than running in on demand. But we also know that spot instances may not be available, in which case we run our service in on demand instances, but then the moment spot instances are available, we switch to spot instances. This type of automation does not exist in a cloud provider, so we had to implement. We have automated quite a bit across our stack to achieve cost reduction. Let me talk briefly about what is next for Razorpay. We aspire to continue to be the most loved and trusted fintech. We started with global expansion last year. We launched our payment gateway solution in Malaysia, and we are looking to expand more in Southeast Asia and other regions over time. We are also spending time looking at new regulations that have come up. For example, the Data Privacy Act in India, which is very granular, and we are looking at implementing that in the next few months. We're also carefully inspecting whether our current architecture can take us to the next level. We are thinking of adopting cellular architecture, which reduces the blast radius, which allows freedom for engineers to develop features in an agile manner, deploy faster, and expand to various geographical locations much faster and innovate more. It is still day one for us. Thank you for the opportunity.
Welcome back from the break, and thank you for being with us today at Data at Scale. And thank you to Murali for this inspiring session where we learn how Razorpay is preventing DDoS attacks, how they're preventing fraud, and how they got to 4 nines of availability and are innovating the financial tech industry.
Our next speakers are from Meta. We'll hear from Dan and Mohammed about how Meta is leveraging generative AI to improve incident report. Diana is our product manager in Infra, and Mohammed is a software engineer in monitoring and observability org. They will share some of the experiences bringing generative AI technology to improve our incident response. Let's hear from them.
Hi, everyone. Today, we want to share about how we're leveraging the newest technology to rethinking how we work here at Meta, specifically around incident response. At Meta, we serve over half of the world's internet's population on a daily basis. And this is not something that we take very lightly, and which is why we always want to make sure that fewest incidents occur, and when they do, we try to resolve them for as fast as possible. Because every second that our site is down means that collectively we might be losing tens or even hundreds of years together. And not only is that number staggering, we also hear directly from our users about how this is impacting them. Users relied on us to connect with their loved ones. In addition to that, we also serve millions of businesses that have their livelihood depending on our systems working. In fact, we're not the only party that actually gets notified when an incident happens. In the past, we have heard about police and government agencies being informed when our site is down. But keeping our site is no easy task. Our infra has been scaling in the last 10 plus years with our products and the users that we support. And there are a lot of dependency between services, there are high complexity in our systems, and there are just large number of change happening at any given time. So it's very easy to make unintentional changes that actually have cascading effects that developers may not be aware of when they're making that change. Hi, my name is Diana Xu, and I'm one of the PM here at our infra. And today we want to talk through a little bit about how we're rethinking how to manage incident at Meta leveraging GenAI. Specifically, some of the problems that we already know about and have been working on for a few years. Before we dive into too much of this, let's take a step back and look at how we think about a lifecycle at incidents. It starts all the way from it happened to being actually discovered by the team, to finding out and trying to figure out what is the root cause, what is the actual problem that we need to go and solve, to then quickly mitigating it and bringing the site up. Today, this is actually very manual, and because of that, it's very stressful and frankly, a little chaotic. So how do we help? Specifically, that start with investigation phase. Right now, this might look like a straight line, but in reality, there are tons of people jumping in to help. We have one group of people, that's called them existing responders, who might already be involved with this after the incident has been notified. And they're trying to actually start jumping in and looking into specific paths of the things that they're experts on. At the same time, we have many new responders jumping in and helping. For them, they have to quickly figure out what has already been happening so that they can help. So from the responder's point of view, it's actually more like this. In that first, they need to be onboarded. They need to dig through all the history and chat threads about what's going on, what has already been ruled out. They also need to then jump in and help identify the root cause. And then once we find a root cause, multiple people might have to all work together to mitigate it. So that actually creates an interesting tensions between these group of users. If you look at the right side charts between the two groups, you'll notice that for new responders, today, they're actually cannot move forward and they're blocked from helping without getting some information from the existing responders first. But from the existing responders' point of view, a lot of time they're already trying to investigate one or multiple issues that could potentially be the cause. So for existing responders, we're actually distracting them. We're trying to pull them back of the things that they're working on so that they can go answer some questions. So this actually creates a bad experience for both sides. Now I'm going to hand off to my colleague, Mohammed, to talk through a little bit about some of our efforts here.
Thanks, Dana. Hi, everyone. I'm Mohammed Farag, a software engineer working with Dana in the data org around incident management. As Dana has explained, onboarding responders to incident is critical. We need help of everyone that we can get to get incident resolved. We can't do everything on our own. Yet this onboarding process is not that easy. It's difficult. And it's not also something new. This has been on top of our mind for a while now. We have tried various solutions, yet nothing is a silver bullet. Everything has trade-offs. We actually tried multiple approaches, some of which are asking responders to provide regular summaries of how things are going during the incident. These summaries can be then used by onboarding responders to onboard faster without having to go through everything, all different sources of information. Yet, it can be a bit difficult during a stressful incident to remember to provide these updates. And even if you remember, it can be very stressful that sometimes you are too focused on trying to resolve the incident yourself that you actually don't want to actually share these summaries. And let's not forget, even if you provide these summaries, a few minutes later you tried something new, you learned new pieces of information, things have changed. We even tried assigning roles. For example, an individual would be assigned a journalist role. This means that that individual would help onboard responders, protecting existing responders from any follow-ups or questions or reach outs, while also helping the responders that are new to the incident on board. Yet, this doesn't really scale that well. Teams might be short on hand during an incident, and even if they are not short on hand, in larger incidents you can have tens of in parallel work streams going at the same time. So what do we do about it? We found the latest advances in LLMs to be one opportunity for us. So we started using it to help onboarding responders. And the flow for onboarding changes significantly from what Diana have shown a few minutes back. So what has changed? As you can see right now, once a responder is paged, for example, around the purple box, they no longer have to actually go through tons of different sources of information. They have a real-time generated summary of the incident given to them, containing all relevant information from the ongoing discussion to current status of the system. And we don't stop there. They also have an LLM chatbot or LLM assistant that can answer all their follow-up questions if they have any, helping protect the existing responders' time and speed up responses to the onboarding responders. As you can see, there are no connections between the existing responders and the onboarding responders anymore. The onboarding responder get immediate responses from the LLM assistant, and they quickly onboard to join on the investigation and the response. But let's dig deeper. How did we actually do it? Once a new responder opens the incident management tool, they are faced with a real-time generated summary. It gives them that quick overview to catch up on the incident. It can contain different sources of information, and it even references the different sources of information that were used to build up that summary, so that the responder can actually check these sources of information to verify or even get more information on that aspect. And once they are caught up, they might have follow-up questions. They are able to utilize Meta's internal LLM-based assistant. It has access to many different artifacts within Meta. It also has access to the ongoing discussion for the incident, enabling it to answer any follow-up questions. This enables responders to get all their questions answered, and immediately they are able to jump in and help out with the investigation. Now, onboarding is a mean to an end. We don't want to have everyone just for the sake of having them in there. It's not a party, I assure you. And now that we have the folks that we need to actually get their help to actually investigate the incident. But investigation comes with its own different challenges. Let me pass it back to Diana, who will talk a bit about some of these challenges.
Thanks, Mohammed. Now that we already help the responders being onboarded, now let's take them to the next part about how do we quickly find the root cause of an issue and diagnose the actual problems. First, let's try to understand what are the different causes for our incidents. That might be something around deployment and code changes. It might be something where our system is just overwhelmed, or there can even be physical failures. For today, let's focus on the first type, which is code changes. And specifically, this is actually really hard at Meta because of our unique architecture of our system. Specifically, that we have something called monolithic repo. So what that really means is, even though we support various different type of apps and features, for most people and most developers, they're actually making changes into a single repo. And what that means is that at various times, there are thousands of changes happening at the same time. And then in addition to that, there are many dependencies. Then multiple developers might be making changes throughout that dependency change. So multiple changes happen at the same time. So what that means is that it's actually really hard for responders to try to figure out what's happening. First, they have to figure out what type and what might be the cause of this particular incident. They have to look through various of data, various of logs, to then try to narrow down. But they figured that out. We already narrowed down that this is caused by code changes. Now, throughout the code changes that we talked about, they have to try to correlate the data that they're seeing together so that they can further scope down these issues. And even once they get to, say, hundreds of codes, now they have to try to figure out and interpret different lines, trying to understand what is the impact of these changes. And all of this can be very time-consuming and very manual. And without it, they cannot go and mitigate the issues. Now that being passed to Mohammed to talk through some of the innovative way that we're doing to help in here.
Thanks, Diana. As Diana have shared, we have tons of challenges to identifying the root cause of an incident. And having tens of thousands of changes a day doesn't make it any easier. So how do we go about to actually pinpointing that single change that actually triggers the whole incident? Fortunately, we have a very solid data model around incidents in Meta, and responders have been doing a good job collecting data across historical incidents. We were able to analyze historical incidents to identify a few trends and patterns that we evolved into a set of heuristics to build a correlation between a change and a given incident. Some of these heuristics are very simple. For the given systems that were impacted, are the same set of owners actually own the files that were changed. Some are a bit more complex. For example, the given API, which was impacted by this incident, what files does it depend on it? It's basically a runtime dependency graph. Using these heuristics, we were able to reduce the search space significantly. We went down from tens of thousands of changes to a few hundreds. This is a 100x reduction. Yet we didn't see significant changes in terms of accuracy. Now, this is amazing results, but we need to be a bit realistic. It's infeasible for responders during an incident to actually go through hundreds of changes when time is of essence. So what do we do about it? We started looking at these changes to understand a bit how to reduce it further. And one thing we noticed in common is most of these changes were actually relevant to the system that's related to this incident or was impacted by the incident. And maybe it updated the system or changed some of its dependencies, but they are all related somehow. So what we needed were a way to reason about the changes, how they might alter the behavior of the system and lead to this given incident. This was an opportunity where we thought we can tap into LLMs as a way to reason about changes. So we started using a 7 billion Llama 2 which is a fine-tuned version of Llama 2 on internal data and internal business context. This model was fine-tuned also on the use case of identifying incident root cause. We will give this model all the relevant context for an incident, along with the changes that we have found from the previous step. And the model would be able to give us the most relevant 5 or so changes that might be the root cause or the trigger of this incident. Now, I mentioned Llama 2. You might be aware that Llama 2 has a limited context window of 16K tokens. So how did we go about it when some of the changes can be very large and we might not be able to fit in all few hundred changes? This is where we combined a divide and conquer approach with a ranking via election. Basically, we split these changes into pages each of a size of 20. Some pages might be less than 20 changes. And for each given page, we pass it to the model, along with the information from the incident. And we ask the model, what are the most likely 5 or so changes out of this set? This ends up giving a set of changes that are usually around 5 or less. Now we have eliminated around 75%, 15 changes from each page, which is good. What we do now is combine each 4 or so pages to get back a page of size 20. And this gives us a new set of pages of size 20, as you can see, similar to the yellow box in the diagram. Of course, we may have multiple pages of size 20 at this step, and this is where we keep repeating on this cycle until we end up with a single page of size of 5. Of course, the final output might be less than 5 changes, and this is the set of changes we give back to the responder to examine, which may include the root cause, hopefully. Now, in theory, it all sounds very exciting and promising, but how do the results look like? I will hand it back to my colleague Diana to share some of the exciting results we have found through our work.
We're super excited to share some of the early promising results that we're already seeing in both onboarding as well as root causing the problem. For our onboarding efforts, we're starting to see responders reacting very positively to the real-time summary as well as answering the questions to help them quickly figure out what is happening. Almost half of our incidents are already relying on this, and then 86% of the time people find it to be super helpful. Now, moving on to root cause analysis. This is where we're starting to see very promising results, where within minutes of an incident being created, we can actually find the potential root cause 42% of the time. So what that really means is that as a developer, instead of spending hours trying to figure out, dig through various data, codes, etc., you actually have this information right off the bat to help you and help reduce that stress. Obviously, with this new technology, it wasn't all smooth. And there's a lot of learnings that we have to look through, especially using this new technology, where AI does tend to hallucinate a bit. So how do we, especially during an incident time, where providing wrong information can be catastrophic? This means that we're taking people precious time to look for the wrong cause so that they're not actually looking at what they actually need to do. So with that, we come up with 3 principles with our design as how we are leveraging GenAI. The first one is we have to be very transparent to earn the trust. We need to make sure that we're very clear about the limitations about AI and then helping people understand where is it getting its information from. Secondly, it needs to be very explainable. People need to be able to follow along AI's logic as well as the step that it's taking so that they can understand what to watch out for, and then also avoid providing a single recommendations so that they can also try out things themselves. Third, we need to make sure that it is very actionable. Not only do we want to help responders during the time or the cases that AI can help, we also want to up-level them. We want to up-level their skill sets. So when the time that AI cannot help today, they can actually bring the knowledge along and then do this manually in a less stressful way. What we see is AI have the potential to really change how incident can be handled at Meta, in that it can help across all stages of incident, all the way from when it's happening to the time that it's being mitigated, where we can bring down this entire cycle from hours to minutes. And not only that, because our infra supports the entire developer life cycles, we also imagine new ways that having this information can actually proactively preventing incidents from happening in the futures. How do we learn about this to make sure that these learnings are applied into coding development? We have a saying here at Meta that the journey is only 1% complete. And we very much believe that is true in this case. We have a very new technology that really is going to change how we work, especially around incident management. Thank you, everyone, for taking your time and learning with us.
Thank you, Diana and Muhammad, for this session. Yelena, what I take from this is that by accelerating incident response time, we help over half of the world's population connect with their loved ones and so many businesses that rely on our platform. How about yourself?
For me, this was like really exciting talk because it offers a glimpse of the future where GenAI really revolutionizes how we do day to day, including the incident report. Next talk will be from Snowflake, and they will share what it takes to bring such product to the market. Nathan and Calvin, principal software engineers in Snowflake, will share how they bridge the gap between the research and product development to bring LLM-based solutions to their customers. Let's hear from them.
And after this session, we're going to have live Q&A with all the speakers you've heard from so far. Go ahead, use the chat feature at the AtScale website and share your questions with us to hear from the speakers.
Hi, I'm Kelvin So, a principal engineer at Snowflake. We at Snowflake recently released Arctic, a top-tier enterprise large language model that pushed the frontier of cost-effective training and openness. To continue with the openness, we would love you to share some of the detail of how we use Snowflake data platform to prepare training data to build an efficient, intelligent enterprise LLM. Training LLM such as Arctic takes a lot of data. The data can come in many different types. For example, there can be public data sets such as Hugging Face and Common Crawl. Or you can bring your own private data set as well. This data set usually come in many different file formats. Some of the data set is also very huge, as you can see in the green Common Crawl box. Each of the Common Crawl usually is tens of terabytes, and there's almost more than 100 of Common Crawl snapshots. So we are talking about petabyte of information here. It's not sufficient just to collect all this data and fit into training your LLMs. The other important aspect of building a good LLM is to have very good data qualities. There are many strategies of filtering out low quality tokens to improve your training your models. So I have done this type of work at previous company, both at search startup, Niva, and at Google. What you put into the model is what you get out. The higher quality to improve the data, the better the models becomes. Traditionally, one write a lot of custom code and data processing pipeline to work to prepare the data into LM trainings. As an example, there are many open source data set or frameworks such as WebPajamas. They usually come with a data set with signals such that you can filter low web quality tokens to increase the quality of your LMs. Alternatively, you can also work with a web crawl like a Common Crawl yourself and use distributed processing framework such as Dask or Spark to do custom processing pipeline. Usually, once the data process is done, you usually write this data into S3 in AWS or other file-like object in the cloud. The post-processed data is then used in training large language models. As an engineer at Snowflake, we took a very different approach. What we do instead is to natively do this within Snowflake to prepare the training data for Arctic. So one may ask, why does it make sense to do all this data preparation work in Snowflake? Many people know Snowflake for their cloud-based data warehouse, they are very good at doing distributed data analysis on very large data set. It also has very powerful government and data lineage capability out of the box. However, usually ML data engineer don't associate Snowflake with LLMs. However, with combination of capability of the thing that I just mentioned, actually is ideal for data processing for LLMs. In today's talk, we will demonstrate how we can use Snowflake to process large volume of data efficiently, besides the efficiency that I just talked about. Doing an LLM data processing on Snowflake also gives you additional benefit, which include provenance, data lineage, as well as policy enforcement on your data. So once the data is in Snowflake, it also unlocks fast iteration of your data, which is critical to build a very good LLMs. We have built tools on top of Snowflake using Streamlit to help us iterate data quality within hours. In this talk, we will show you some of those tools and how it helps us to enable fast iteration loop within Snowflake. Here is the agenda for today. Nathan will first walk us through a data creation process with a practical case study of building this data sets over code. He will demonstrate how you can prepare this data efficiently, provide provenance and data lineage, as well as enable policy enforcement. I will also talk about some of the tooling to enable rapid experimentation to improve our data quality on top of Snowflake, which is critical of improving LLM model qualities. Now I will pass to Nathan. He will deep dive into practical case study on building data set over code.
Hi, I'm Nathan Wiegand, a principal engineer working on Arctic. Today, we're going to build a data set over code as an example of how we manage training data for Arctic. In order to train the best possible LLM, you need to source the right data, you need to clean and process that data, and you need to have the right model architecture for efficient use of that data. Today, we'll focus on the data processing part of that story, specifically how we curated our code data set. There are many sources of code datasets online, for example, at Hugging Face. Let's just focus on how you prepare your dataset after you've acquired it. When building our dataset, we want to make sure that our data is of highest quality. We start by loading the data into Snowflake. At first glance, you might think of a code dataset as being a table with 3 columns: repository name, file name and path, and the file contents. But we observed that about 20% of the file contents are actually duplicated into at least 2 files. So instead, we break the table into 2, file metadata and file contents. This saves a lot of storage costs, and it makes some queries a little cheaper. Also, structuring the data this way makes it really easy for us to do file-level deduplication because we've already computed the content hashes of all of the files. On the left, we have the file metadata table, which is keyed by repo name and path and has a column called the content hash. On the right, we have our file contents table. It is keyed by content hash and has a column called contents. The thing to note about the table on the right is that each row occurs exactly 1 time. It is globally unique across content hashes. Now that we've loaded the data, let's talk about data cleaning. While there are many aspects to data cleaning, I'll cover 2 here today: file level annotation and repo level deduplication. Since at the end of the day, these code files become examples as we train our LLM, our goal is to annotate the files with quality annotations that we can use for further processing downstream. For each signal, rather than computing it more than once, we want to permanently associate it with the file in the file metadata table. This makes things more efficient. The Big Code project suggests several data cleaning attributes in their paper, Star Coder, May the Source Be With You. Let's cover how we built 2 here. First, let's build a signal called isNoisyXML. There are many files in our data set that are machine generated or that use complex XML schemas as storage format. We might find these to be less interesting for our LLM. So what we'll do instead is we will annotate these XML files and say that they're noisy if they are not XSLT files. XSLT is a programming language that happens to be stored in XML. Here we create a simple new column on our file metadata table called isNoisyXML. Let's read the query that populates it from the inside out. First, we process the file contents table to find all code that appears to be XML files. These are files that begin with a special marker, which is less than $XML. We could be more defensive about whitespace or capitalization, but for this example, we'll just use the starts with function. This now returns a list of all content hashes of files that we believe are XML files. We update our file metadata table's new isNoisyXML column when the content hash matches the one in our set, but where the file does not have an XSLT file extension. Here in just a few lines of SQL, we were able to populate a new document annotation that combines concepts across two tables. While the last example was very simple, let's do something way more complex. Let's add a new attribute, which is about detecting whether or not a file is noisy HTML. We'll say that a noisy HTML file is one that's probably not generated by a person. So that's an HTML file where fewer than 20% of the characters in the file after rendering are still visible. Now, doing this in SQL would be very, very difficult. So instead, it would be really great if we could rely on one of our familiar Python libraries like Beautiful Soup, and we could do just that. Snowflake supports running Python scripts along with Java, JavaScript, and Scala over your data via a mechanism called user-defined functions, or UDFs. Here, we define a new UDF called %HTML UDTF. It takes one parameter, which is the HTML content, and note its return type. It returns a table, and the table has a column, which is %HTML visible, which is a floating point number. Here is the body of the function. This is just a Python program. The main thing to note is that we define a class with a single method called process. Process yields new rows in that table that we're outputting. The yielded tuple must match the return table definition above. So when we yield, the first value of that becomes the %HTML visible in the definition. Here, we're yielding the ratio of the length of the rendered text using Beautiful Soup to the length of the original content. If you were to execute the overall query, you would get a new function in your environment. So let's see how you'd use it. Let's assume that we've already created the new column, which is called %HTML visible, and we only need to populate it. Zooming in on the innermost query, we first get a list of all of the HTML files on which we want to apply our content. So that's the innermost filter. By keeping the percentage instead of the label here, we make it easier to do downstream experiments later. So rather than hard coding 20% now, we can see how 30 or 10 affects our actual LLM. As I already mentioned, identifying file quality is necessary, but it's not sufficient to build a good code data set. We also want to investigate repository quality. Many repositories are clones or forks of other ones. And many times, these don't even have meaningful changes. They're just exact duplicates. So we're going to say that two repositories are exactly the same if their file contents are exactly the same. So how we do this is we use the arrayAgg window function. We just aggregate all of the content hashes of all of the files in the repository. The one difference of that simple aggregation is that we order by the content hashes themselves. This gives us a total ordering over all content hashes in our array. This makes comparing arrays really simple. But we actually don't need the arrays themselves. We just need to compare arrays for equivalence. To make computation easier, let's just consider the hash of the arrays instead. After we've collected all of these hashes of arrays, we'll call them repo hash. Then all we need to do is group all of the repos that share the same repo hash and pick one. For our purpose, any one matters. They're all exactly the same. So let's pick the first one alphabetically. So that's what first value does for us here. The final product of each of these transformations is a new column on our file metadata table. Here's an example of a schema that we might generate. Repository name, path, content hash, these are familiar. We've also added our new isNoisyXML and our %HTML visible. At this point, we've covered how we can efficiently, both computationally and operationally, clean our data set. Now to talk briefly about how we can track data lineage and how we can manage policy enforcement within our data set. We can maintain provenance and data lineage by borrowing an old trick from the database community called database migrations. The first idea is that we never allow an engineer to have write access to the database. This means that you can't add columns or rows or do any mutations whatsoever. Only our production account can do that. Engineers write SQL files. These are our migrations. that say how to mutate the data in the manners that which we've described above. These get then implemented in order in an atomic manner. So at any time, we can guarantee that we know exactly how any column was built by simply looking at the migration files in our Git repository. When we output data for our LLM training, we have a similar problem. How can we be certain that the training data for our LLM was produced in the way we thought it was? For this, we use the same idea. Exports from the database must be done by production jobs that are verifiably built. The exports write to an S3 bucket that only they have write access to. The engineering team can read it all they want. Along with the data, the production job annotates or adds a data card that specifies how the data was generated, by what process, and on what date. With this information, we're able to go all the way from the training data that goes into the LLM for training, all the way back to how exactly it was generated, making the whole system fully reproducible. For code dataset in particular, being able to have certain policy enforcements are a requirement. For example, here, we want to make sure that our code data is appropriately software licensed. For this, we'll use a view. A view is like a named query that we can issue again. In all of our database exports, we will not query file metadata and file contents directly. Instead, we're going to use this view that enforces our policy. This way we can be certain that all data written to S3 is always data that's within policy, and we know how to regenerate it. So far, I've talked about how we implement quality and policy filters on our data. But it's equally important to talk about how we iterate on these quality labels to see exactly which data yields the best downstream result. I'll hand it back over to Kelvin to give examples of how we build tools on top of Snowflake to iterate on data quality.
Thanks, Nathan. That was great. But what I'm going to tell you is even more important than what Nathan just told you. As I said at the beginning of the talk, what you put in the model for learning is what you get out. The high quality of your data, the better the model becomes. So in the next sessions, we'll cover some of those examples of how to build tools to enable rapid experimentation on your data. First, the benefit of having your data in a data warehouse like Snowflake is the ability to query your data. For example, with a simple query, you can ask, what is the top repo in the coding dataset within seconds? In this case, as you can see in the screenshot, FreeCoderCamp is the most popular repo in GitHub. It's very easy to query the data different way to understand the shape and property of your pre-training data. Now we know that FreeCodeCamp is our most popular repository. Why don't we manually embed some of those examples here? This is just a simple /star query. You can see that in the screenshot here. Each of the row here is show the content of the code. This is super helpful to build intuitions on what exactly you are putting into your training your models. In this particular UI, it may not be the best way to quickly browse through your data, given there's quite a lot of other information we are showing in each row. To make browsing even better, we built a simpler Streamlit app. Streamlit is an open source Python library that make it easy to create and share custom web app natively within Snowflake. In these particular examples, we built a simple app with a drop-down menu to select the type of language you want to browse randomly. In this case, we select Python code, and then you can quickly click on the next items to view a bunch of random examples. This is very helpful to build intuition what we are actually have in our data set for training your models. To extend the app a step further, we add 3 buttons: bad, neutral, and good. This allows us to rate the content quickly in one of the 3 categories. This rating is then written back to Snowflake database. This is very important because this enables us systematically evaluate if the dataset is good or bad. Also, once the feedback is written into Snowflake, we can also use it as label to training a classifier to filter out all the bad content. In my past job, our team also built something similar, a human rater tool outside of Snowflake. Just doing a simple rater tool will take up weeks with a small teams. But with Streamlit, I was able to do this in less than 3 hours, even though I'm new to Streamlit. Of course, there's still quite a lot we can do to improve it to a fully functional human-rated tool, but this is probably a good start for many people. So a lot of time, you will also want to apply different operation or filtering strategy on your data set to improve the quality of your data. For example, in the StarCoder paper Nathan mentioned earlier, they describe a method for PI filtering on your coding corpuses. I always ask, once I implement those filtering, what is the precision and recall on those changes? How many items did I affect with the filterings? In this particular diff tool we built, we can see that we implement PI filtering in the code and store the content with a PI removed in a different column in Snowflake. In this particular app, you can see the original content on the left and the content PI removed on the right. And there is a diff view at the bottom where it's showing that Kelvin Sol, the author of the code, is correctly removed and show it in red color. This quickly allows us to go through many examples to see if you are doing the filtering correctly or incorrectly. This helps us to build intuition and also improve our filtering mechanisms. Finally, I would want to show us our eval dashboard. To iterate our data quality, we run hundreds of data ablation to validate if the changes, such as the filtering that we have built, is helping with model qualities. When the experiment is run, we store the eval result within Snowflake. And we also build a simple eval dashboard to help us track progress of our experiment that we run. In this particular screenshot I'm showing here, we ran 4 different data ablation runs. Each ablation run usually gives us many metrics, which you can see on the table on the right. And then we use the average of those metrics to plot a bar graph, which is shown on the left side. This can all be done within Streamlit. So with that, we have seen that we have built a data processing system for Arctic LLM within Snowflake. Rather than having to worry about efficient compute, data provenance, data lineage, as well as enable policy for your enforcement on your data. We were able to build all this within Snowflake and leverage Streamlit integration for rapid experiment with different means of improving the data qualities. Looking ahead, our goal is to continue to push on the boundary of what is possible with LLM trainings. And then we are already start exploring with different way of generating synthetic data as well as other sophisticated filtering techniques. Now I will pass back to Nathan to give us some teasers on what other things we have done in Arctic.
Thanks, Kelvin. We've released a series of blog posts detailing how we built Arctic, from data acquisition and composition to how we optimize GPU coordination and training. What we presented today is just a brief overview of how we use the Snowflake data platform to manage our training data for Arctic. Because we were able to iterate quickly and confidently using the tools and techniques that I described, and using the data exploration tools that Kelvin described, we were able to ship a fantastic model tailored for enterprise use cases, going from an empty directory to a shipped model in under 5 months. Please see our cookbook series linked here for in-depth discussion of our model architecture, training infrastructure, data recipes, and much more. Thank you for your time today. We're really excited about the future of LLMs, and we're super grateful for the opportunity to speak with you here today.
Hello, everyone. It is my absolute pleasure and honor to welcome our speakers, Pedro, Murali, Diana, Mohammed, Nathan, and Kelvin, to our live Q&A session today. Before we get started, I'd like to remind all our viewers that you could post your questions to the AtScale conference link. And with that, let's get started. And thanks to everyone who've already posted your questions as well. I'd like to start with you, Pedro, on the composable data management systems. The first question here is, the community behind Velox has very rapidly grown since it was open source 2 years ago. What do you attribute to that?
Yeah, no, thanks for the question. Happy to be here as well.
Yeah, I think on the open source part, because Velox was kind of such a large effort and such a large endeavor, one of the first things we did when we started the project was kind of looking at the community and talking to other companies and trying to understand like what other companies have similar problems and would be kind of willing to partner with us. So kind of in the very beginnings of the projects, like we chat with most other companies, and we started seeing that it was a very, very common issue, or like something that many other companies and organizations outside of Meta would like to invest on. So I think we started talking to Intel early on, to Voltron Data, to Ahana, and they all kind of had efforts around kind of trying to make compute engines more efficient. So we ended up creating a collaboration between those companies and saying like, well, let's not do all those kind of invest on those projects in a decentralized way, and like let's rather kind of join forces and start working on this. So this is kind of how we started, and then I think the more companies joining, of course, the faster the project started making progress and like adding features and becoming a lot more mature, and then like other companies started to join. But I think it was just this idea that was something very it's a problem that many companies had and many companies really were willing to invest on. So that just kind of resulted in a very kind of quickly open source growth, which we're very happy about.
Awesome. That's a wonderful story of a flywheel effect with open source partnerships. Thank you. The next question we have here is for Murali. When we think of Razorpay and the fast growth that it's had, a lot of companies focus on product market fit. So from your view, what are some of the things that you would recommend taking care of while we're in that phase, so that when you scale, things become easier to handle?
Thank you, Manju. I think the first thing is about the architecture to be done better at the design phase itself. It's when you are chasing AMF, we call it the 0 to 1 journey. You need to ideate faster and eliminate bad ideas sooner, but then quickly it turns into 1 to 10 and 10 to 100 type of opportunity. So at that time, rewriting your service is quite difficult to do. So I would always start with proper design and make sure that the operating principles are very clear. For example, in my organization, I focus on engineers to know that security is the top priority. Make sure the design takes care of security. Make sure compliance is clear from the starting, because company may not exist if compliance is not taken care of. Reliability, availability, performance. Think through all of that. But only when the basics is covered, innovation happens. So that's the learning, and we have been trying to do that at Razorpay.
So relying resilience and security first, infrastructure. That's awesome. Right. Thanks for sharing that. The next question we have here is for Diana and Mohammed. How do you ensure, so this is about your talk on how GenAI can be leveraged for incident response. How do you ensure responders are not misled or distracted?
Yeah, we share a little bit about this in our talk, and we really want to make sure that we're very transparent about what are the data that the AI are leveraging to give the response. And then we're also trying out new things, such as having AI share the confidence level that it has, so that the user is also more aware about kind of around using the information that AI is passing back. We are asking everyone to do the verifications and making sure and not just taking the answers and the response from the AI blindly. Mohammed, anything that you want to add to this?
Okay. Yeah, thank you for sharing. I think adding the confidence level for the responders is super helpful. I agree. The next one we have here is on Arctic, and the journey, how you went from 0 to 1 in 5 to 6 months is pretty fascinating. Would love to hear from you in terms of what are some of your future plans in the data processing for Arctic.
Oh yeah, I can speak to that. Like So one thing that we recently just experimenting is like, so we recently in Snowflake, right? We released something called LM function in GA. So what it really helped us is that like in the talk, right, we talk about briefly about how you can use the streamlet to kind of label the data bad and good. But like right now, like with the function, you can actually prompt any model we have there and then ask to do some rating for you and in much more scalable way and cross track with the human label that you have, right? Then you can do it much more efficiently on any of the data labeling annotations to help to increase the quality of your pre-training data. The other thing that we are exploring how to generate synthetic data that will also help with like getting a better models. Yeah.
Got it. Synthetic data and human intervention.
Yeah.
That's pretty
Yeah,
awesome.
like doing data annotation with like the LM functions, like prompting the other models to help us to label or annotate the data. Yeah.
Very cool. Thank you. We'll go back to Pedro. There's a few live questions coming in. Pedro, what do you mean that Velox is engine agnostic while it is an execution engine by itself?
Yeah, I think what we mean by execution engine is more like it's a library that we provide that's able to execute operations in a host, right? So it's not like by execution engine we don't mean like the actual entire compute engine. It's just the library that knows how to execute those things. And I think the idea is that we can integrate the same library into multiple compute engines. And I think this idea of being engine agnostic means that you can actually take Velox and integrate into different systems with different semantics, with kind of different characteristics, because the library is fully extensible. So you can actually take Velox, integrate into Presto, and then you use kind of the entire Presto ecosystem, the Presto service, and then you kind of configure and add all the extensions needed for Velox to follow the exact Presto semantic, but you can do the same thing in Spark, you can do the same thing in other different systems, right? So the kind of the right mental model is just assuming that this is a library that you integrate with other services.
That's awesome. Yeah, thank you. The next question we have live here is from Morley, right? So you talked about Razorpay being the end-to-end platform for merchants. From a privacy perspective, like what is your view on providing merchants with information about customer behavior, such as the chance for return to origin?
Thank you. It's a very good question. What we provide to the end consumer is a faster checkout option called as Magic Checkout. Razorpay as a payment gateway is providing this payment gateway functionality to multiple merchants. And you can imagine that when a consumer is buying from a website, they may not be comfortable sharing their contact information and payment information to a random merchant website. So this Magic Checkout option with consent allows consumers to let Razorpay pre-fill the addresses, contact information, payment information, and so forth. Along with that consent, they also agree to let merchants provide better service to them, including remembering the payment options to give a better experience. So essentially what we are providing to the merchants is an option to configure which payment method shows up first. So instead of payment on delivery option, merchants might choose to show a credit card or debit card on the top. So that's how we handle with privacy. It's with consent.
Got it. Yeah, I think the consent is an important factor. Thank you. The next question we have here is for Diana and Mohammed. Do you, with all the talk about AGI, right? Like, do you expect at some point investigations will be completely automated?
Yeah, this is a great question, actually. Like, I while we are far off from that point, what we are trying to do is like see where we can start building small building blocks to get us to that North Star. It might be far-fetched that all of this will be completely automated through AI, for example, but at least maybe it would cover the biggest operational burdens for engineers, where engineers can verify the work and either approve, decline, suggestions, and so on. So maybe we are far off, but we are working toward like a North Star that's close to assisting engineers so that they don't have that much workload.
Got it. Yeah, I think it's maybe hard to put a time frame for solving this problem. But definitely exciting. The next question is for Nathan and Kelvin on Arctic. Does this generalize to multimodal?
Yeah, I think so. So there are two components of what we talked about. There's the data storage part of it, and then there's all of the data annotation, slicing and dicing, making sure that your policies are enforced and all of that. For any data source, no matter what it is, no matter how big the blob, there's always going to be metadata associated with it, license, whatever category it belongs to, for example, science or humanities or whatever. And so all of that can certainly be stored in the database and processed in the way we described. There may be stuff like hypothetically, if we went big and outside to videos or something like that, where those blobs are a little larger than what you might normally want to put in even an analytical database like Snowflake. That might be stored outside, but the core idea is the same. The idea being the metadata and the attributes are the things that you want to filter on and process. That all can be stored in this manner.
Yep, that would help from a quality perspective.
Exactly.
Very cool. The next question I have here is on the Velox presentation, right? How is the experience and cost of migrating existing data systems over to Velox?
Yeah, I think that depends a lot on the engine you're integrating Velox to and kind of how kind of broad the integration surface is. So we see, I think maybe naturally, like when you're developing new engines and you kind of want to do that using Velox, it's a lot easier, right? Now kind of integrating Velox and kind of doing a surgery into existing engines, that's something that gets a little more complicated, especially if it's something that already runs in production and something that already has a very large footprint. Like those the integration themselves are very complex projects that might take quite some investment. So I think usually the mental model is what value does that value, and does the value the integration add actually pays the investment, right? But I think maybe the answer is kind of depends. Of course, integrating Velox into kind of very mature SQL analytic engines, like I think I mentioned in the presentation, like Preston, Spark, like those are probably the most complicated integrations just because the surface is pretty broad. Like it uses all the entire library, like all the SQL operators we provide. There's also a lot of discussion that it needs to provide the exact same, it needs to follow the exact same dialect and provide the same semantics to users. Otherwise, it might break backwards compatibility. So even when things are stable and hardened and well tested, we need to make sure that it kind of provides every single kind of semantic issues and kind of a bug by bug implementation of those things, right? While in some systems, like sometimes you're just reusing the same memory layout or just the serialization function, like this is a kind of a lower level integration. It's a lot easier. It kind of depends on, I guess, like the maturity of your engine, and depends on how many things and what's kind of the complexity of this integration.
Yeah, I think that's very fair. And once you get to a composable place, then you're able to move faster. But getting to that state, especially when you're not in that state, is going to take time.
Yeah, and we already have a few examples of new engines we developed inside Meta that kind of came after Velox. It was already mature, and I think that's what we're trying to get, and what we mean by this engineering efficiency. Like in those cases, we're able to move much faster. Now, kind of retrofitting this into existing engines, it's a much higher bar, but it still makes sense in some cases.
The next question we have is for Murali. What are some recent product innovations at Razorpay that you are most excited about? A sneak peek.
In terms of technology use, in the last 1.5 years, the GenAI has come to a place where we have figured out how to provide good functionality to customers and for engineer productivity internally as well. For example, the DevOps organization is able to debug live issues in Kubernetes by using LLMs. So essentially, we have put our SOPs as part of prompt files, and we are able to debug things much faster. And we have made it self-service for our engineering organization, which is pretty cool. We also are doing Docs AI, for example. Developers that are looking forward to integrate with Razorpay have to go through API documentation figure out how to integrate and whatnot. That is a long process in general. We are able to cut that down and also build a one-click migration from our competitors. We built that with the LLM. So given the API specification, we're able to convert the code. These are quite exciting. So I'm looking forward to doing a lot more there in terms of providing functionality to our customers.
That's awesome. Thanks for sharing those. I think this is also very close to the incident management work that we've been doing at Meta. So the next question is on this topic, right? How are you thinking about the balance between human and automation when it comes to incidents?
Yeah, so I think we in both short-term and midterm, we really see that this is we do need help from both, but also trying to figure out how do we go from right now where it's very manual to maybe perhaps a stage where AI is doing a lot of assistance with human making the decisions. And then ultimately, can we get to a place where the role might be switched a little bit, where AI might be doing some of the planning, especially learning from experts, learning from past experience, but with human kind of in the loop and make sure that AI is doing the right thing and making sure that there's some traceability in the way to continue guide the AI in the right place, but continuously changing the percentage and balance between manual to AI to kind of in between.
Yeah, makes sense, right? I mean, I think it's we want to make sure that what we do well, like we are very clear about it, and where we're not quite there, to highlight that part. Cool. The next question here is for Arctic, Nathan and Kelvin. At this scale of data, right, the pre-processing becomes super important, right? So what are some of the pre-processing steps, pre or post-processing steps, do we need to do outside of Snowflake?
So I'll take that. Snowflake is really great for what we're doing is data orchestration and filtering. But beyond this, there's this black box, which is training the LLM. And for that, you have to take your textual data as it is now, eventually multimodal. You need to do this step, which is tokenizing, which is replace some set of character sequences with a unique ID. And once you have that, there's this very important step, which is to come up with a data composition, which is how much of web data, how much of code data, how much of Python versus SQL do you put in the model at this phase of training? And then after that, how do you iterate? And Kelvin showed a little bit of that in his talk, where we train these smaller models, these ablation models, all out of Band, all out of Snowflake, but we evaluate them, and then the output of those models and the output of the evaluation goes back in. And so that allows us to complete the loop. And so that's the theme we've been hearing from a lot of people, which is the real value that we're all trying to drive for is the ability to iterate quickly. And so that's the thing that was the motivation behind what we did around Snowflake. But the idea is the only way to get to a good LLM as quickly as possible is to shorten the iteration loop as much as possible, especially when training on GPUs takes weeks at a time. And so right now, the large part of the work is figuring out the right data to add at the right time. And for that, we're doing a lot of experiments out of Band.
Got it. Yeah, that iteration time means everything in training. That makes a lot of sense. Cool. So we're back to a question on Velox. So Pedro, after a common execution engine, which is Velox, and a new storage format, Nimble, what are some of the common components of the composable data stack that Meta is focusing on?
Yeah, that's an interesting question, right? Yeah, I think we've been really focused on execution engine. Like you said, we've been evolving the file format. I think in theory, technically, all those things would make sense to kind of just unify and provide common libraries. I think the question is usually how much value would that add, and what is the cost of doing those things? Right? So I think at the end of the day, is based on ROI, like what the return would. What is the return of the investment over those things? So that's why we started on the execution engine, just because there's a lot of CPU power, there's a lot of resources that go into those things. So if we can make this cheaper, like it actually provides a good return over the investment. I think usually when we look at other parts of the stack, that's sort of the discussion, like, okay, this makes sense. And I think technically not many people disagree that this would be interesting to build, but the question is more like how do we prioritize those things? I think answering the question, we had some internal efforts on unifying, or at least kind of starting to unify the language part. I think, of course, like if you had a single SQL dialect that you can provide to users across engines, this would be ideal. And I don't think anyone would disagree that this is, kind of the best case scenario. I think the question is usually kind of what's the cost and how much effort goes into that. I think part of that is, well, we can only do that if you actually have the same engines running the same code bases so that they can provide the same semantic. But we had some internal efforts on, at least like for the engines that already provide where we want to follow the exact same SQL dialect for users, like at least providing libraries that can provide kind of parsing capabilities or kind of providing a more unified IR. So we have some of that internally, but it's still, I think it's not very clear like what's the value. So I think that would probably be the next project in terms of different parts of the stack. But I think maybe the underlying message is just like we need to be careful about what are the things that are worth doing and how much return that would provide.
So lots of work going on, fairly early stages. So okay. The next question we have is for Murli, right? So how do you propose handling operations at scale, right? So there's the process component, there's the tooling component, there's the people component. Like what would you say is the biggest challenge? And what are your thoughts on resolving them?
I think you have listed all three of them correctly. So it goes in cycles, though. I would say the most overlooked ones are usually done in the early stages. For example, is your architecture tightly coupled? Because initially it might allow you to ship faster, but then after a while it becomes harder to ship features, and then it will cause customer experience problems with regressions and so forth. So I would say start early on with better design so that you can have velocity later. Do conduct periodic operational reviews so that the engineers are exposed to the problem so they can work on resolving them, or at least have more time before something becomes big, along with the things that you mentioned that allows you to scale.
Thanks for sharing that. Diana and Mohammed, from a scaling Meta's infra with GenAI perspective, like how do you see incident management changing with AI?
So I think multiple factors will happen. Like from one perspective, right now our focus on like how can we improve response through LLMs and AI, but we are also trying to discover and explore other areas. Like similar to what Diana mentioned during the presentation, like how do we prevent these from happening in the first place? Like how do we integrate these as a part of like the developer ecosystem so that we are not late into the process? So I think over time we will see this being integrated into many parts of the developer workflow. And also we expect that as time passes, we will be able to reduce the workload on the responders and hopefully be able to provide more accurate back our data and maybe even verify these assumptions or these decisions before sharing them with the end responders. Again, it's a long journey, but like, as Diana mentioned, we are 1% done.
That is absolutely true, the 1%. Cool. I think we have maybe time for one last question on Arctic. What is the scale of data that you have used this within Snowflake?
Yeah, thanks. I will take that. So yeah, so basically, like for Arctic, we use roughly 3.5 trillion token to pre-train our models, right? And then like I would say roughly about like half is like processed through Snowflake, right? And then like if you think about that, right, that's like roughly like each of the token usually is 2 bytes, so it's like we are talking about terabyte of like
maybe 2 to 4 terabyte of data being processed through Snowflake, and then kind of like pre-train our models. So yeah.
Awesome. So it's like 50-50. Okay, got
Yeah.
it. I believe that is all the time we have. We're going into a break right now. Again, thanks everyone for joining us today for Q&A. We appreciate your time. Thank you.
Thank you.
Welcome back. This was a lovely Q&A. Thank you to all of you who submitted your questions, and thank you to the speakers for sharing their thoughts with us.
Next, we will hear from Ken and David from Meta. Ken and David are software engineers in our infra and focusing on privacy and security. Today, they will talk about the Meta's data graph and explain how it enables privacy and security compliance and the use cases. Let's hear from them.
Imagine being able to view data infrastructure as a giant graph and use it to benefit privacy and security. My name is Ken Lin, software engineer at Meta. Today, with my colleague David Tai, we'll share how Meta built a large-scale graph for its offline data system and use it for privacy, security, and other use cases. So what is Meta's offline data systems? Meta operates large-scale offline data systems across data warehousing, stream data processing, and service monitoring and observability. Collectively, they support use cases across analytics, stream data processing, and also service monitoring and operation. They are also important upstream of machine learning. Batch and streaming data are key sources of machine learning features. Enforcing privacy and security and other data management and governance concerns are very important for this data infrastructure because the volume of data, the scale of the system, and the wide variety of use cases. In order to do it effectively, we need to rethink how to represent this vast data and the system and in a way that is understandable, expressible, flexible, and scalable. The high-level idea is to view this infrastructure as a global graph. We use it to map out the system and the assets in the system with unified metadata representation and link the assets by their relationship and flow of information. Let's take a warehouse as an example. Data warehouse is like a factory of data processing. Pipelines read data and output data. The input data are produced by upstreams. The output data are consumed by the downstreams. Think of a set of pipelines like a room. The inputs are moved in, the outputs are produced within the room, and there's also fine granularity flow of information within the room. In order to establish such a representation, we need to model the data flow as a graph and establish relationships between the assets and represent those assets use generic metadata representation. We call such a graph representation data graph. In today's talk, we'll first share how we build the graph, and then share how we apply it to privacy and security problems. We'll close the talk with more use cases. I'll hand over to David to talk about how we build the graph.
Thank you, Ken. I'm David Tayeb, and will now dive into how we build the data graph. As Ken alluded to, the main idea is to map out all the diverse assets in the warehouse and the data flows as a giant global graph. This will allow us to perform powerful graph analytics at scale and further explore the rich relationship between those assets. It will also enable us to create new visualization that provide new insight into those relationships. Looking at the data model, we want to retain as much important information as possible about each and every asset and each and every flow. For that, we use a simple yet very flexible data model. For the vertices, we store the category of the vertex, which is either an asset or an evidence. An evidence is a process that generated that asset. For the type, we have the class of assets. There's hundreds of classes of assets in the warehouse, for example, Hive table, or a Spark query for an evidence. We store an external unique identifier, which uniquely identifies in a human-readable form using a meta-wide convention consistent across all our internal storage. An internal unique identifier, which is a big int for efficient computation, and finally, a metadata, which is the free-form map key-value pairs of attributes that provide contextual information about the vertex. For edges, similarly, we use a type, either a flow or a containment. A containment is a parent-child relationship. A table has multiple columns, for example. A source vertex node, a target vertex node, and an evidence node. The evidence represents the process that generated that edge. We store the granularity, whether it's table, column partition, partition level. And finally, similar to the metadata in the vertex, we store the annotation, which is a free-form map of attributes, key-value pair the same way, that provide contextual information about the edge. So now, what is data graph used for? Well, there is multiple use cases. The first one that's most common, it helps answer fundamental questions about the data flow. Does my asset X flow to asset Y, even though X and Y are not directly related? Does asset X contain sensitive data? This type of question, very important, very fundamental. For the discovery and scoping, we want to start from a given set of root nodes that we've carefully identified and create a subgraph of downstreams where we follow the data that has been copied into those downstream nodes. For data understanding, what is the real edge of the data? Are there cumulative cycles? And finally, label propagation, which is a very important use case. Given a set of root nodes, which we carefully labeled with some annotation, we want to propagate those annotations according to a given set of rules. Those rules can be very complicated. So now let's look at how lineage signals are collected. There are mainly 4 types of signals. Instrumentations, where we go and add the code to our data processors, our compute engines, to call directly the lineage API with very careful information about what's going on within the data processor. Very, very important. For static analysis, for some data processors which are well structured, like SQL processors, we use deep SQL parsing to extract high precision column level lineage. Annotations will go directly into the data pipeline code. Those annotations, high precision annotation, are automatically generated sometimes and reviewed by human expert using a very well-defined governance workflow. The last one is log analysis, where we scour all the logs in our runtime components to find those edges that couldn't be found. This is very important for measuring recall and find those unknown unknowns. Let's look at an end-to-end workflow. On the left, you have the lineage ingestions. The data flows are collected either from the compute engines, SQL and so on, or the identity-based access event. And then those events are sent to an interface to be processed and stored into a data graph. In the middle, you have the discovery engine, which is the code that is responsible for traversing that graph. But it also uses and fuses the signals from another component, which is the unified asset metadata, which contains a bunch of extra information about the asset. Like, for example, user data classification or semantic classification. This data is fused into an iterative API, which we're going to explain in a minute, to provide and create the highest precision and highest coverage possible graph. We wrap this up on the right in the control plane with a standard API for convenience to our users, and a set of standard measurement to make sure that the precision and recall comply with a set of requirements. So let's look at a use case study, output closure. Output closure is about understanding how sensitive data flows into our graph so that all the assets in scope can be properly controlled and access controlled. To do that, we really need high precision and high recall. And we built an iterative discovery API to account for the imperfection of the graph. At each iteration, we automatically discover all the assets that are high confidence. And then we stop and we fuse the signals with different sources, the unified asset metadata, the different granularity, to generate one-hop candidate. Those candidates are that sent for curation, either auto-curation with some heuristics that are predefined, or for the most ambiguous cases, we use manual curation when we send to human expert for adjudication. So what does the iterative discovery look like? Well, here on the left, you see the first iteration where the graph is grown to a certain extent, and we stop, and then we use the boundary expansion to try to find the one-hop candidate by fusing those signals. And then we send it for curation. That's the first iteration. Then we rinse and repeat, and we grow the graph using the same methodology once those one-hop that we were not sure about have been discovered. And so on and so forth until we've grown the graph to the entire warehouse. So let's look at a little bit of more privacy-related usage. We talked about output closure, but there's also input closure when we want to prevent sensitive data from entering specific zones. You have retention, we talked about, data understanding to follow the graph, to try to propagate those semantic annotations, and transitive closure when we want to answer asset X relate to asset Y, even though they are very far apart. So privacy is only one use case that benefits from data graph. Let's now look at how the data graph can also benefit security with my colleague, Can Lin.
Thanks, David. Just to recap, David just shared how we build the graph and apply it to privacy. The graph idea is not limited to privacy. So here I'll share how we apply it to security. Security of the offline data system is a broad topic, covering areas across building services security, data encryption, and access control and management. Here we'll limit our discussion to access control with a focus on scaling it. Data infrastructure is a collection of data stores, computer engines, and data tools. To scale the access control, we first build the unified metadata representation of all the assets and enrich them with annotation in different dimensions. If you are familiar with attribute-based access control, aka ABAC, this is called Object Attribute Store. We also built unified permission service to make the access control decisions and let the data systems enforce those decisions. In ABAC terminology, the former is called policy decision point, and the latter is called policy enforcement points. Here, we use data warehouse as an example, but the principles apply more broadly for other cases. In order to make policy decisions, there are two key components: the data architecture and data annotations. The data architecture models the hierarchical data model of the data warehouse from namespace, table, to column and subfield. Data annotation enrich the asset with metadata in different dimensions, including semantics, what's the meaning of the data, actor, is that about employee, user, or business, ownership, who is responsible for the data. The data architecture allows us to build a coarse to fine granularity control. And the data annotation allows us to build dynamic controls based on attributes. Over the years, we've built control at different granularity, from namespace to subfield. If you are familiar with Apache Hive, you probably know that a column can be a structure by itself, a practice commonly used at Meta. To support the need, we build the control all the way down to the subfield level. The metadata annotations also enable us to do dynamic access policies. In order to further optimizing the control based on the graph idea, we need to understand how the data is produced, processed, and flows through the system. As previously shared, a data warehouse is a set of pipelines that read from inputs, produce outputs, and the inputs are produced by upstream, and the outputs are consumed downstream. At Meta, we represent a set of pipelines by a concept called data project, which shares business context and has identity associated with it. From this perspective, the graph is interconnected data processors and its reads and writes. Data processes, together with the data, form a boundary of data access needs. When operator needs to work on the data, it provides the context and the scope of the data access. Graph is hierarchical in nature. We can drill down and roll up the data processors. As previously mentioned, a data processor is a set of pipelines. We are building fine granularity identities, which allow us to zoom in to a smaller section of the graph, establishing finer granularity context. By zooming in, it also enables us to do finer granularity control. This model is not limited to data warehouse or tables. As previously mentioned, the batch and stream data are key sources of machine learning features. We can apply this to machine learning, where the input are features and the processing are training jobs and the output are machine learning models. I'll hand over to David to close the talk.
Thank you, Ken. So let's review the 3 key takeaways from this presentation. First, we discussed how the data graph and unified asset metadata opens new ways of modeling offline data systems and flows. Second, we also discussed how data graph enables us to go beyond individual objects and create boundary, think room in a data factory, and afford us another level of access control. We also discussed how certain aspect of the graph is imperfect. This is due to the heterogeneous scale and the diversity of the system. And to minimize having to make difficult trade-off between coverage and accuracy, we saw how it's important to rely on human in the loop. As the quality of the graph gets better over time, this will ultimately translate into a more efficient and automated experience for engineers. So again, why both accuracy and coverage are important? Because simply said, coverage drives compliance, and accuracy and usability drive efficiency. Maximizing both is hard, but certainly possible. Going forward, we want to also look at how, beyond privacy and security, we can also use the data graph for more classes of problem. Data corruption recovery, when we want to identify downstream of assets so that they can be backfilled properly. Data ripping, we want to look at which data has not been used for a long time and may be ready for being deleted. Capacity management, we want to optimize data placement based on usage. And data pipeline debugging, which are looking at the upstream of an asset, allow us to a better visibility and debugging capability. So this concludes these talks. Thank you for listening. Merci.
Thank you, David and Ken. This session was a great opportunity to learn about some privacy and security controls Meta is building and how critical they are for our everyday.
Up next is Francis from MotherDuck. Francis is gonna take us through some of the old assumptions and what happens if we challenge them or change them a bit, and how we think about interactive analytics. Let's hear from Francis.
Hey everyone, my name is Frances Perry. I've been working in big data infrastructure for about 15 years. Originally, I was at Google working on some of our internal data processing. Before that shifted over into Google Cloud, and I was on some of our products there. Currently, I'm an engineering leader at MotherDuck, which is a small data analytics startup here in Seattle. Now today, we're going to revisit a couple of those foundational assumptions that we had when we first designed distributed big data infrastructure. Things have changed around us since that point in time, so we should reevaluate the way we process data and change that as well. I'll start by introducing you to emerging technologies, including DuckDB, which is an open source data analytics engine, and MotherDuck, which extends DuckDB into the cloud. And then finally, we'll end with a demo of a data-intensive application that combines both of these and gives you instantaneous data visualizations right there in your browser. Now, I'm sure we could go further back, but for today, we'll just start in around the year 2000. At this point in time, data center technology was changing. Instead of expensive mainframes, data centers started relying on cheap off-the-shelf components that you could go down and grab at Fry's Electronics. Right? There were lots of machines in these data centers, but they were just cheap and they had a high failure rate. So what that meant is, as software engineers, we had to adapt to how we built for these data centers. The MapReduce paper came out in 2004, and it described an algorithmic pattern that could easily scale across multiple machines, even when those machines failed on us. And it was flexible enough to support a large range of use cases. Almost any algorithm you could think of could be just twisted slightly and run in the MapReduce framework. So MapReduce could scale. It could scale to more machines and even more. And if our data got bigger, we could split it even more finely and throw more machines at it. Right? This power was really obvious to everyone in the community. So the open source community took these ideas and started Hadoop, which really founded a full ecosystem of distributed data processing systems. Soon enough, everyone was able to use these systems to process all the data they could eat. Everyone, that is, who knew Java and knew how to manage a cluster and all the things that came along with these large distributed systems. So some tools started hiding these big distributed systems. They put them behind what was a much more familiar SQL interface. And at this point, people started to really understand how to interact with and use these tools. We've seen, particularly in the last few years, this explosion where data analysts can become data engineers. So more and more people are now able to participate in data processing. All of these people processing all of this data and spending all this money on those big distributed systems. But a lot has changed since we first started building those systems. So for example, our machines look fundamentally different than they used to. Moore's law had a good run, cramming more and more transistors on a chip, right? But eventually the laws of physics do get in the way. So now what we're seeing is machines start adding more and more cores. So today, if you want more compute capacity, you don't just throw another machine at the problem. You go off and you get a bigger machine. So those machines from the MapReduce paper, they had 2 cores. 2, right? Today, on my way home, I can grab a gallon of milk and a 96-core machine over at Google Cloud, right? The size and scale of the machines that we're operating with is just fundamentally different. Even this MacBook sitting right here on the desk in front of me, right? It's got 8 cores, 16 gigs of RAM, and most days I'm using it as a web browser, right? It's incredibly overpowered for what I usually do with it. So our machines got bigger. But all that big data just accumulated, right? We kept adding to it. We kept generating it, and it's all sitting there. It's floating in our data lake. Occasionally, we're going back and we're looking at that whole accumulated archive. We're doing backfill, or we got it for compliance reasons. We're retraining new machine models, new AI models. But most of the time, we're not using anything but the most recent chunk, right? Most processing that we do is over a working set that is just a tiny portion of the full data that we have. MotherDuck's co-founder Jordan came from Google BigQuery, and in his experience, 99% of queries that were run ran over less than 10 gigs of data. And 90% of those were even less than 100 megs. So if you take that idea and you sit and noodle with it and go take that concept of larger machines and smaller working sets, that's what gets us to DuckDB. DuckDB is an open source data space started by folks over in the Netherlands in about 2019. Now, it's built quite the growing community in the last few years, and that's really because it has 2 unique features. DuckDB is not distributed, full stop, right? And it won't be. It's built to be embedded inside a single host process. There's no dependencies, but it's still got lots of performance tricks. There's some clever memory management, some vectorized query execution. So it's still going to be performance focused, but it's not going to get performance by scaling out across more machines. And people are really starting to notice how much you can still get done in this model. So about a year ago, someone benchmarked DuckDB on their laptop, and it outperformed a 16-core data warehouse, just with the MacBook that was already there, sitting on the desk, It was going to be idle otherwise. So that essentially gives you free processing, right? You don't have to pay for what's already sitting there. The second feature of DuckDB is really the portability. So DuckDB compiles into WebAssembly or WASM, which means it can run directly in all your major web browsers. No installation necessary. If you got a web browser, you've got a fully powered database now. So we can take both of those core technologies, but it's still purely a local solution. So MotherDuck takes DuckDB and takes it up a notch by moving it into the cloud as well. Not instead of, but as well, right? So here's DuckDB running on your laptop. Sometimes you want the flexibility of the cloud. You want to shut that laptop lid, you want to automate your job. You need something slightly beefier than what you've got in front of you, but still not a full distributed system. So MotherDuck runs a personal instance of DuckDB for you in the cloud. Now, this cloud instance of DuckDB is going to coordinate with your local instance. The query planning that's being done is joint, and it's moving data back and forth in intelligent ways to really optimize for getting as much processing done as close to you as possible so that you're getting that interactive and instantaneous feel. The DuckDB instance in the cloud is dynamically scalable, so we'll handle vertically scaling it within a single machine so that you're only paying for what you actually need there. But as much as you can, you're using your local laptop. Now, MotherDuck also provides a storage abstraction that looks just like a friendly local file system, which is what DuckDB expects. But actually, under the hood, right, it's a fully built out cloud storage system. So we've got a layered format there that's going to allow us to do things like data sharing, zero copy clones, time travel. So now we've got a pretty comfortable setup for our duck to do their data analysis. But if you've seen Mighty Ducks, ducks fly together. There's a flock involved, right? So MotherDuck has a flexible data sharing model that lets you bring along your other friends, and they can each use their own interface of choice. Maybe it's the Python SDK, maybe it's the command line, and they'll get their own instance of DuckDB in the cloud, their own processing playground, dynamically sized for whatever query load they're running. But together, you're now all able to query away over that shared data set. So let's get to the demo and actually see DuckDB and MotherDuck working together. We'll do this through the lens again of a data-intensive application. So these applications are everywhere. They're what helps you and me interact with and understand the data that's all around us. Google Analytics is sort of your most standard example, right? Helping webmasters everywhere understand how people are using their website. But I have one on my mobile phone that helps me manage my money, right? As engineers, we're all using observability tools to understand and keep our services running. Anywhere where you're playing with a graph, you're pulling sliders, you're thinking about and analyzing, and your brain is working away as you're driving and playing with this data. Now, traditionally, to build a data application like this, you'd use what we call a three-tier architecture. You've got the client-side code that's running on the user's laptop. Then you're going to make calls through the slow and twisty paths of the internet to get to your application server, right? Which then is going to query your database. Client, application server, database. Those are your standard three tiers. Now, when you have this, you're likely going to need a team of folks to keep it up and running. So they're adjusting the caching logic so things feel snappy in the browser. They're patching the database, monitoring the server, right? Now, it's not surprising. A lot of places now offer serverless. So what that will do is let us carve out that second tier, that web app. But with MotherDuck and DuckDB, you can go even further and drop below 2 tiers. So the way we're going to do that is we're going to think about the data that we're using. When we interact with it, we're often starting with a coarse filter query that selects a working set that's going to be much smaller than the original data set. So for example, visitors to a specific part of the website, or my spending just over the last year. Now, it's totally reasonable to take that smaller data working set and ship it to the laptop and continue to interact with it and do your detailed exploration locally, right? And because you're operating locally, your queries are 0 milliseconds away. They're right there. And you're going to be able to get this instantaneous back and forth. And together, that's going to unlock entirely new ways of visualizing and interacting with your data. But at the same time, even while you're getting that power of your local laptop, the cloud's still there, right? It gives you a seamless transition between your local working set and the full data set. So if you want to adjust the working set, move back a year in time, or add in additional data, right? You're still just using those same happy SQL queries that you're used to. There's no adjustments you need to make, and you can rely on MotherDuck to go ahead and do that hybrid query planning across the laptop and the cloud to give you that seamless experience. So with that, when we do it in duck math, which is very important, we had the client and the database. We've taken the database tier, we've split it in half and moved half of it to the client. So that leaves us with one laptop and half a database. That's a 1.5 tier architecture. So let's get into this demo. So we'll be using DuckDB and MotherDuck, but we'll also add in Mosaic, which is a tool that lets us do some pretty cool data visualizations. So the data set that we're going to dig into is Seattle weather. You can see we've got a lovely spring day here in Seattle. And we'll dig into how we can play with this to better understand if Seattle weather really is as bad as everyone says it is. All right, so here we have a web browser. All I've done is load this demo page, right? I haven't installed anything locally. And what I'm going to do real quick is just log into MotherDuck with my web token. I'll just get my token, copy it back here, and this is authenticating me to MotherDuck as myself. And now I will grab the Seattle weather data set. So at this point, what's happened is that we've gone to the web, down to MotherDuck, downloaded enough of this data to be able to begin visualizing. And from this point on, this visualization is going to run locally on my laptop. So every time I move my mouse, we're going to be seeing new SQL queries running on DuckDB on my laptop and updating this presentation so fast that it's going to feel completely instantaneous. So in this graph, just to orient you to the data that we've got here, we've got temperature going up our y-axis and months of the year across our x-axis, and then different kinds of weather in different colors. So yellow is going to be our elusive sun here in Seattle. You're going to see a lot of that blue rain, little gray fog, smatterings of purple snow. But we can just now sit and play with this data. So I can just go and grab my mouse and I'm going to be able to grab a sliding window across a subset of data. And at this point, I've just run a new SQL query over just that portion of the data, and I can begin playing with it and interacting with it. So I've proven to myself our summers are gorgeous. Let's check out the early spring. And the late fall, definitely a little more rainy. I can filter down, take a look at just snow. Yeah, we might have a white Christmas, but maybe not. But if we go back to sun, I can prove to you right here, right? It's not gray all the time in Seattle. We have sun year round, just along with all that rain. All right, so bringing this back, what you've seen today is that we can drop those old assumptions, and that's going to enable us to think differently. Our data might be big, but more often than not, we're only using that little chunk of it. And the machine shapes that are sitting right there in front of us, they've fundamentally shifted from when we first designed our data processing infrastructure. So let's take that old, big, heavy, expensive distributed data processing infrastructure and catch up to actually how data is working for us today. We want to use the cores we've got right in front of us. And by doing that, we're going to experience instantaneous results, queries that are 0 milliseconds away. And that's going to let us fundamentally interact with our data in a different way. And it's going to save us money, right? I've got those cores. They're just sitting there running my web browser. Let's put them to work for us. So the cloud's still there when we need it, right? MotherDuck will make that seamless for us, but we don't have to live with our head in the clouds. It's there to serve us, not confuse us. All right, so thank you so much. I hope I've intrigued you to learn a little bit more about different ways of thinking about data processing. Please go check out DuckDB, MotherDuck, and Mosaic. Thank you so much.
Thank you, Francis. Elena, what stood out for me was the way that Francis talked about how hardware back then was designed with some assumptions that are no longer relevant.
Yeah, and for me, it was a great reminder that user experience matters, like especially when dealing with interactive data at any scale. Our next speaker will be Santosh from AWS. Santosh is General Manager of Data Integrations in AWS. He will talk to us about smarter and faster analytics, leveraging machine learning and generative AI. Let's hear from him.
Imagine that you are head of the data platform and your executive team wants to make an informed decision about the latest ad campaign. For that, you need to combine the customer data, sales data, marketing data, social media feed. You want to analyze these data sets and build an executive report articulating the impact of this ad campaign. This is great to get started, but as you talk to your team, your data engineers tell you that they're already struggling in keeping up running hundreds of pipelines that they have. If you talk to data analysts, they tell you that they're struggling to meet SLAs to their business teams. When you talk to your data stewards, they tell you newer and newer data sets are being generated, and they're struggling to consistently discover and govern these data sets in your organization. And finally, when you talk to your business analyst, they tell you they are spending too much time in creating reports and too little time in analyzing the data. I'm sure many of you have faced these challenges at some part of your data journey. Now, the question to ask is, can generative AI and machine learning accelerate insights to your data? And can generative AI and machine learning help you scale your data infrastructure? That is the crux of this talk. But before we get to the depths of this talk, let's briefly chat about generative AI. So what is generative AI? What's so cool about it? Unlike machine learning that focuses on past events and creates the model for predicting the future events, generative AI creates novel content, often mimicking the human creativity. That's the coolness of generative AI. Now, over past few years, having access to vast amount of computational power and GPUs at cloud scale, coupled with the fact that you have scalable data infrastructure that allows you to process hundreds of petabytes of data, and finally, newer algorithms that can help you build machine learning models with hundreds of billions of parameters made generative AI possible. As you can see here, having a scalable data infrastructure was one of the key reasons what made generative AI possible. So what are the key components of scalable data infrastructure? In order to understand that, let's look at an end-to-end data lifecycle. Your data resides in a variety of data sources. They can be OLTP sources, streaming sources, on-prem sources, third-party vendor sources. You want to be able to ingest, cleanse, transform, and integrate this data to find a comprehensive view of your business. You can use something like AWS Glue for data integration. Once the data lands in target systems, you want to be able to catalog, discover, and govern your data sets on a consistent basis. For that, you use AWS Lake Formation or Amazon Data Zone. The data lands in data lakes or in cloud data warehouse such as Amazon Redshift. You can further process and transform these data sets and make the data available for machine learning. For that, you can use big data service such as Amazon EMR, or you can build machine learning models using Amazon SageMaker. Once you build the models or the large language models, you could consume them in building generative AI application using Amazon Bedrock, or you could use them in your business intelligence layer using Amazon QuickSight. This kind of stitches the end-to-end data journey. Now I'm going to take a pause and talk briefly about myself. My name is Santosh Chandrachud. I'm the General Manager for Data Integration. I've been with AWS over the last 7 years, and I've been part of the journey to build, launch, and scale many of the services that you see here. Now, while there is innovation happening across all axes of data infrastructure and many of the services that you see here, we're going to talk about 3 key areas. We're going to talk about AWS Glue. That means we're going to talk about data integration. We're going to talk about Amazon Redshift, and we're going to talk about Amazon QuickSight. So let's begin with data integration. Data integration is a very first step before your data analysis can begin. If you get this step wrong, you'll end up with incorrect results. That's the reason this step is extremely important. In order to do data integration, data engineers build data pipelines. Data pipelines are hardly scalable. They're often brittle. Data engineers end up writing and building a lot of undifferentiated machinery to make these data pipelines scalable and robust. They manage infrastructure. They manage the vagaries of source system and target systems and schema evolution and type systems. They also ensure they enforce rules to have high data quality in your data sets. Now, while a lot of this undifferentiated heavy lifting is reduced by using service like AWS Glue, you still need to author a lot of business transformation and business logic, which is relevant to your workload. For example, you could use visual authoring tools such as Glue Studio to build your data flow diagram that mimics your business use case. Or you could write code using notebooks or code editors. But the question to ask here is, can you simply build highly scalable, robust pipelines using English? Last week, we announced Amazon Q for data integration. With this, you could use natural language to build data pipelines. It also acts as a subject matter expert at every step of your data integration, right from discovering your data sources, to writing your transformation logic, to operationalizing your data pipelines, to also give you contextual help in troubleshooting your data pipeline failures. It also creates highly performant logic for first-party data sources such as S3, RDS, and Redshift. Let's look at how Amazon Q for data integration works in action. You can simply ask a question about what are the best practices for using AWS Glue. It provides you comprehensive documentation. It provides you references that you can double click. Now you can start building a pipeline. You can join data sources in different locations in S3, apply your transformation logic, and write in a highly optimized format. It generates the code that you can then convert into a job that can be a part of your recurrent data pipeline. As you can see here, by just writing few English statements, you're able to generate a starting point, a boilerplate code, which is highly performant, that helps you accelerate your data integration process. Now, building highly scalable and reliable data pipelines is a great start, but your quality of insights is as good as quality of your data. In a recent survey with a bunch of chief data officers, they cited data quality or lack of thereof was the primary reason they could not realize the potential of generative AI. Now, detecting and enforcing data quality at scale is a challenging problem. You want to be able to create data sets which are accurate, comprehensive, complete, have referential integrity, and are also not stale. You want to be able to write your business logic that reacts to your latest state of your business. In order to solve data quality, data engineers often write data quality rules, and they evaluate the rules against the data sets as and when the data sets arrive. Often these thresholds are static in nature. That means it only reflects the static part of your business. Anything that has dynamism in your business is missed when you write these rules one by one. For example, if you're a candy store, the data quality rules will always create false positive as your candy sales surge in the month of October. Getting these static rules to work is a time-consuming and erroneous task. It just slows your business down. So the question that we should ask is, can machine learning be leveraged here to learn hidden patterns in your data sets and automatically recommend you the right dynamic rules? We added this machine learning capability in Glue. The way it works is, with this ML capability, AWS Glue Data Quality Engine automatically starts scanning key statistics about your data sets. It builds algorithms and machine learning models that can further refine based on your inputs. Once we get these models in place, the data quality ML engine starts recommending you insights about your data sets. Then it also recommends you what dynamic rules you should be installing in detecting and monitoring your data quality. Let's see how all these things work by watching a short animation.
Here I have a New York taxi dataset data pipeline. It takes this data on a daily basis, aggregates it, and loads it into another S3 bucket. Now, to enable data quality checks, I simply add the data quality transform. I really have no time to configure data quality rules now, so I'm going to use the new ML capability to help me build rules I can evolve later. For this, I'm going to add an analyzer called row count. Analyzers gather statistics and detect anomalies in your data. This is going to gather our row counts, learn from the patterns, and start detecting anomalies. I've run this job a few times now for each new dataset, and Glue has learnt the patterns of my loads. Simply go to the Observations tab and notice that Glue Data Quality has already generated an observation about the abnormal drop in row count. You can also visually see this from our graphics.
As you can see here, machine learning can be used to identify hidden patterns in your business. So to recap this part of the section, we saw how you could build highly resilient and optimized pipelines using generative AI, how you could enforce quality in your data sets using machine learning. Finally, these data sets land in your data lakes or data warehouse. That brings us to the second part of the discussion, Amazon Redshift and how we can utilize generative AI and ML capabilities for further acceleration. There are two classes of problems that we see here. The first class of problem is writing highly performant SQL is hard. It's essentially hard for users with less technical skills. So we want to be able to use generative AI to accelerate data analysis for less technical users. The second challenge that you face is having consistent query performance at scale, keeping in mind the best price performance and meeting your SLAs is a hard problem. And can we use artificial intelligence and machine learning to simplify this journey? Let's look at the first problem. Imagine you had generative SQL capability, which will allow you to simply ask questions in English and it generates optimized SQL for you. You can get started very quickly. This applies to both technical users and less technical users. You can also discover more about your data sets by simply asking questions in English. Here, you're also prompted sample questions that give you an idea about what's contained in your data sets. For example, you can define one of the starting questions and ask about top 5 users that purchased tickets last year. You can get a highly optimized SQL query and its output. You can further refine this by asking further questions, again in English. Find important sellers. You get highly optimized SQL output. Now, once you're satisfied with your data analysis, you can simply use the SQL statements in other parts of your data journey. Now, while you can author SQL quite easily, and it benefits all classes of your technical users, having a consistent performance out of your data warehouse is a hard problem. If you remember in our old times, you would have a database administrator who would improve performance of your database and keep it consistent over a period of time. That meant he or she had to go through a lot of background tasks and background processes to optimize your databases. This is not an option at cloud scale. So invested in AI-driven scaling and optimizations that we call autonomics. The autonomics engine behind the scenes scan your query patterns, data access patterns, your concurrency patterns, your time of the day patterns, and build strategies that can accelerate your queries and offer the best price performance. There are 3 broad strategies that we deploy. The first one is automatic table optimization. With these strategies, autonomics recommends you physical design, your sort keys, your distribution keys. It also chooses the right encodings for your certain column based on the data contained in them. It also does background processes such as automatic vacuum and deletes, and it relieves you of any of the offline processes that you would need to carry on your behalf. Now, this alone leads to up to 40% performance improvements. The next set of innovation is about automatic workload manager. Your workload changes depending upon seasonality, time of the day, number of active queries that you have. The question to ask is, can you have an optimal query throughput for the resources that you have? For that, autonomics starts scanning your query patterns and your resource requirements for a given query and builds algorithms and machine learning behind the scene. So as you're presented with set of queries in a given quanta of time, It impacts this query based on the resource requirements that it will have in terms of memory and compute. That allows you to get consistent, predictable performance from your compute resources. It's also aware of SLAs. Certain queries might be of higher priorities than the other queries. As an example, short-running queries are more delay sensitive than the long-running queries. It automatically prioritizes those queries behind the scene. Finally, sometimes your compute is just not enough, and it scales out and scales in your compute infrastructure based on the priorities that you have set. For example, you may want to optimize for cost. In that case, the scaling follows a different curve versus you've set up the scaling policies optimized for the best SLAs. In that case, it follows a different scale in and scale out strategies. This brings us to the third part of the autonomics, which is automatic materialized views. With automatic materialized views, you create materialized views to accelerate certain parts of your queries. Materialized views essentially pre-computes your queries so that your queries perform faster. Behind the scene, autonomics engine scans for such opportunities and builds and identifies queries that would benefit from materialized views. It creates the materialized views, auto refreshes it, and even updates it as your query patterns change. Finally, it simply deletes these materialized views if it determines that materialized views is going to cost you more money than the performance. As you could see, by deploying autonomics capabilities, you give consistent performance to your business users, your predictable SLAs, and your dashboards render blazing fast. That brings us to the third part of our talk, generative AI in Amazon QuickSight, our unified business intelligence at hyperscale. There are three challenges that you face. The first challenge is, how can you generate reports without spending too much time and energy? Because that frees up you to do creative analysis about your business. Second challenge that you face, once you share these reports and dashboards, can you enable less technical users to unblock themselves as further drill down questions and also customize these dashboards? Finally, can you simply ask an abstract question such as, is this ad campaign creating the business impact I care about? And you get an entire data story and impactful analysis presented to you. Let's start with the first leg. Here you want to be able to generate a calculation using English. You get presented with complex mathematics that you can use to start building your visual. Once you build your visual, you can start modifying that visual and customize it using English. For example, here you're converting the bar chart into the table format. You're also customizing the colors. You're adding more columns, such as the earlier column that you pre-computed. With this, you're able to build your report blazing fast. Now you build the report, you want to be able to share with broader set of business users. Now, as you share this report, the business users would like to know what's contained in them. You present leading questions and data previews so that they can understand more about these reports. In this case, they're trying to learn about best performing products. They want to analyze the performance by profit instead of number of dollars earned. They also want to understand the year-over increase by region. This is the final chart they would care. Now, without having this capability, they would have relied you to build this and shared with them, which slows down overall business analysis process in your organization. Finally, the question to ask, can you create impactful data stories? Here you're asking question, how can I increase profitability and what strategies my sales managers can deploy? You get presented with detailed report with visuals and summary. You can select the areas that you care about and customize the report. The generative AI engine would learn about your preferences and apply them in your next iteration. You can reduce AI verbosity and finally share this report with your business leaders. As with any generative AI and machine learning capabilities, all of these services honor your data access and governance policies throughout the data lifecycle. This brings us to the last portion of our talk. We opened this talk with an inquiry. Can generative AI and machine learning accelerate insights to your data and help you scale your data infrastructure? We looked at data integration process, and we saw how English can be used to author resilient pipelines and machine learning can be used to enforce data quality. Then we talked about Amazon Redshift, where generative SQL can be used to author high-performance SQL statements, and you can simplify scaling your data infrastructure with autonomics. Finally, we looked at Amazon QuickSight, how you can author dashboards blazing fast with generative AI and generate impactful insight and story and build your data stories by simply asking abstract questions. This brings us to the last slide. There's a lot of innovation happening in this space across the data infrastructure and entire data stack. If you want to learn more, please scan this QR code. You can learn about AWS Analytics, you can learn about Amazon Q, or you can build some cool generative AI applications using Amazon Bedrock. Thank you so much for listening to this talk. If you have further follow-up, please reach out to me at the email address listed below. And have a great day.
Thank you, Santosh. Great reminder of importance of scalable data infra to accelerate your business.
Absolutely. Elena, up next, we're going to hear from Amit, engineering leader with Google, about Apache Beam. After Amit's session, we're going to have a live Q&A with all the speakers you've heard from so far. Do submit your questions in the chat. Now, over to you, Amit.
Hello, I'm Ahmed, and today we will talk about how we can beam up your GenAI usage. We will talk from lessons from Apache Beam about usability, reliability, and efficiency. What is Apache Beam? Apache Beam is a data processing framework. It's open source, it's part of the Apache Software Foundation, and has growing usage. And why is it relevant to this community? Because it offers a balanced view of correctness, latency, and cost, and at the same time it has proven itself in cloud, on-premise, and hybrid environments. It also has been heavily used in the machine learning community, and we will talk more about this in this talk. Beam's machine learning journey started in 2017 with TensorFlow Extended. This is an end-to-end machine learning framework. It brought industrial-scale machine learning to Alphabet. Today, TFX pipelines run at Alphabet every day, powering hundreds of millions of inference decisions. And at the same time, TFX has adoption outside Alphabet with large tech companies like Airbnb, PayPal, and X. However, outside Alphabet, there were some headwinds to the adoption of TFX. One of them was TensorFlow was not the only machine learning framework. And at the same time, growing in a diverse set of user base demanded something easier to use. And demand for GPUs and accelerators in general was increasing, and the cost and availability of these devices are limited. And finally, as the number of machine learning frameworks and applications grew, the required costs for ongoing maintenance were increasing, taking time away from core ML tasks. BeamML came to address these problems. It is based on the lessons that we have learned from Alphabet and thousands of small to large scale companies. It offers a standard set of tools to enable machine learning at scale for streaming pipelines. The emphasis on usability, reliability, and efficiency. And it has significant usage growth since 2022 with marquee use cases like Spotify using BeamML to power podcast previews, and they have seen 30 times speed improvement there. Similarly, Credit Karma powers 20,000 features, 200 plus models, and serves inference recommendations for their 100 plus million users using BeamML. Taking a deeper look into the Spotify's ML use case, they have been able to reduce this 110-minute podcast preview timeline under 4 minutes, and that's impressive. But when we look deeper under, we will see a bunch of enterprise requirements. These requirements are centralized ML, explainability, MLOps, and enabling different teams to work with each other. In short, they were looking for an end-to-end ML platform rather than a single ML tool, and BeamML excels at this, it shines in this area. And before getting deeper into the BeamML, I would like to introduce myself. I'm Ahmed Altay. I'm a member of Apache Software Foundation. I'm a director at Google Cloud Dataflow. I like open spaces, open source, Python and data, streaming my hair, and I would like to hear from you. And these are some links to reach out to me after this presentation. Going back to BeamML, BeamML is built on top of three foundational aspects: usability, efficiency, and reliability, and we will do a deep dive on each one of those. At the same time, it offers a rich set of features for ML practitioners. For example, it offers ML predictions with remote or local models with efficient hardware use. It integrates with LLMs. It offers vector DB integrations, integrates with open source LLM frameworks, and at the same time, it generates embeddings for a number of different frameworks. Similarly, it integrates with ML frameworks and platforms like Hugging Face, TensorFlow, PyTorch. It integrates with a number of continuous data preparation tools like TFX and Kubeflow. Finally, it integrates with a number of connecting systems like Kafka, PubSub, BigQuery, etc. to make it easy for you to access your data from anywhere. Let's look at foundations in a deeper way. BeamML is easy to use. So this is a typical streaming ML pipeline. In a streaming ML pipeline, an ML practitioner wants to read data, process this data, to inference on this data, post-process it, and pass the information into downstream systems for activation. And each of these pieces might become a complex software by itself. Beam offers a number of great primitives to address this. However, for an ML practitioner, this might look like the Lego blocks on the left, while they are trying to create this Lego car on the right. As much as it might be fun, and there might be plenty of documentation, what we have seen in practice is people rewriting the same code over and over again, and they are adding inefficiencies and incorrectness as they are rewriting and repeating the same things. Our first key insight here was we would like to introduce common pipeline patterns in a single line, easy-to-use declarative fashion. A first example of that was run inference. Run inference by a single line of code allows you to run any amount of inference workload at production. It works as simple as by taking a declarative syntax to define where your model is and what are your model parameters. It is integrated with a number of machine learning frameworks. It's also integrated with a number of machine learning model repositories. And by using run inference, you can easily do prep and post-processing by adding single-line Lambda functions. And similarly, exception handling in BeamML is exceptionally simple by adding another single Lambda function to run inference to handle any type of error that you might encounter in your production pipelines. By bringing all of this pipeline of read, preprocess, inference, post-process, and activate, each of them become a single line of code. And this is a lot simpler than writing giant pieces of software for each of these boxes. Going deeper into the use case that we have started with, the Spotify use case, it was mentioned that they were using more than 6 models with more than 4 different frameworks. Each of these blue boxes you see in this screen is a model. And this is a true spaghetti in production. And BeamML actually makes it easy to manage this one as well. For example, you can add a single model line to pass your data into 2 different models in parallel. Or you can combine your models in a sequential manner. You can even introduce pre-processing or post-processing functions in between. And if you want to do even more complex things like A/B testing, run inference allows you to very simply pass the same data into different models based on a key. Going back to our original example, inference is only part of the puzzle. We would like to solve other parts of the LLM pipelines, for example, integrations with vector DBs or embedding generations. And BeamML offers out-of-the-box solutions for these ones as well. For example, ML Transform comes with tens of out-of-the-box solutions to do your pre-processing and post-processing. ML Transform also integrates with any number of embedding frameworks that's out there. And similarly, Enrichment Transform, as the name implies, could enrich your data connecting to a key value store, and it will handle all the productionization and scaling aspects of this enrichment work. To wrap up all of this, BeamML is easy to use, and why? The reason is we offer declarative turnkey transforms. These transforms encapsulate really complex use cases like live model updates, support for multiple models with a few lines of code. It serves different parts of the ML lifecycle: pre-processing, post-processing, and inference. It also allows you to combine all of these aspects in simpler pipelines. It integrates with all major frameworks, feature stores, tools, and libraries. It's also production-ready out of the box. Error handling, comprehensive metrics, dead letter queues are all part of the system out of the box, therefore making it really easy to go from experimentation to production with a single line of code change. The next foundational aspect we'll talk about is efficiency. BeamML is efficient. Starting from the problem, hardware is hard. What we heard from users like Spotify, they are swapping models in and out of memory to fit in small GPU memories, and they are compromising on pipeline visibility. At the same time, the cost of running a large number of GPU machines year-round is elevated. For Alphabet, administrative cost of running pipelines with tens of TPUs is high. And similarly, for Credit Karma said that running models sequentially, one at a time, resulted in excessive compute costs. And how could BeamML help with this problem? BeamML works with GPUs natively. It will bring your models into where they belong, GPUs, and it works efficiently whether you have small models. It will bring your small models, position them right next to the processes. Or if you have a single large model, it will put at its own process space and give efficient and easy access across workers. Therefore, it prevents duplication of the large memory footprint. And this equally works well with multiple models. Another place where BeamML helps is right fitting for GPUs. In a typical machine learning processing pipeline, you will see parts that benefit from small workers, that will be parts that really require GPUs, and there will be parts that will require high memory machines. One option here will be to run all of this pipeline in a single environment with the maximum amount of resources, but this will waste resources. Another option will be breaking down this pipeline into 3 pieces, a small worker piece, a GPU piece, and a memory piece. But doing this is error-prone, manual work, and also requires a lot of effort from the user. BeamML makes it really easy by automatically identifying parts of the pipeline and using separate worker pools depending on the resources that's required. In this example pipeline, the first part will run with a worker pool that has small workers. The second part will run with GPUs, and the last part will run with high memory machines. By doing this, BeamML automatically increases the utilization of your GPU worker pool and also addresses the problems with availability related to GPUs. To bring this all up, BeamML is efficient out of the box. It does a number of things automatically for you. It can solve the complex operational problem of memory management, whether you have small models or large models. It will efficiently load, switch, share, use different models as needed by a given pipeline. It will maximize the utilization of scarce and expensive resources, GPUs, automatically. It will use GPUs only where it's relevant, where it will make sense, therefore increases the utilization of your GPU pool. Finally, it will use best practices for cost and latency optimizations automatically. For example, BeamML will dynamically batch elements based on the runtime characteristics of your pipeline. So that you don't have to think about batching, this will be done automatically for you. And finally, BeamML is reliable. Going back to another use case here, Credit Karma, what we heard from Credit Karma is that they are building a self-service machine learning platform. They would like to enable hundreds of data science teams to come and onboard Credit Karma's internal self-service ML platform. Before BeamML, they were experiencing up to weeks to onboard different teams onto their system. And they were experiencing data latencies up to days, and that was reduced within under an hour with BeamML. Finally, with BeamML, they were able to reduce the time to go from experimentation to production to just under seconds. After they have adopted Apache Beam for their internal self-service ML platform, they increased their internal usage by 2x. And how does Beam help with reliability? One piece that Beam helps with reliability is that it helps with reducing the number of concerns that a ML practitioner has to think about while they're running a pipeline. In a typical do-it-yourself platform, a user has to have a concern for their business logic, that's the green boxes in this picture, and they also have to think about how to read data, write data, and they also need to understand the underlying system that's running. In a managed service might take care of more of these concerns and move it to the service provider's domain. But in a typical managed service today, still reading and writing data will be within the domain of users' concerns. What Beam offers is something called managed transforms. Beam could manage complex I/O transforms for the users and move the responsible to service providers domain. In this world, a user will be only responsible and concerned about their core business ML logic, and they can defer everything else about reliability and monitoring and management of the service to the service provider's domain. Next thing, we have dependency management and with automatic driver installations and configurations. This might sound like a small problem, but what we have seen in practice is that this is a part of a source of inefficiency and friction point for lots of users. Lots of users run with bad GPU configurations or spend lots of time trying to install the right GPU drivers at any given time. Beam manages this piece automatically for our users. Finally, it's possible with run inference that users can automatically update their streaming pipelines without stopping their streaming pipeline. What we mean by that is that your users will change, your model will change, your data will change, and you will want to update your system. In a typical environment, you will need to stop your environment and rerun with the new model. In Beam, you can update your pipeline or update just the model part of the pipeline without stopping anything. Beam offers a few options here. One option that it can watch for changes in a model, or it can wait for certain triggers to happen from you to go and fetch an update. To bring it all together, BeamML offers a reliable out-of-the-box offering for you. It makes it easy with declarative IOs and moves the concerns of like complex and moving pieces into the domain of service providers. It makes the dependency management really easy, and it chooses the best drivers and best configurations on your behalf. Finally, it really makes it easy to manage and update running streaming pipelines, including running streaming pipelines models. And why all of this matters? So let's sum it up. One, BeamML has been growing significantly in the past 2 years. With Credit Karma, we have seen that the scale of data processing has grown 2 times since they have adopted Apache Beam. At Alphabet, we have seen that processing of millions of examples across thousands of TPUs without any administrative intervention, and BeamML is today powering Gemini, Edge, Waymo, Nest, YouTube, and other parts of Alphabet as well. Finally, in the Beam community, we have seen a huge spike in interest. Just in the last year, we have seen a 5 times increase in the BeamML-related talks compared to the year before. And what can you learn from BeamML and what can you apply to your own journey? First, building a platform that evolves as fast as your users and ecosystem will make your life easy. ML is a fast-growing and fast-moving ecosystem. If you pick a declarative style, capturing intent, you will give yourself the most flexibility to evolve your platform. Second, build for your users. This is easier said than done. You may not be your ideal user as well. We have made that mistake with BeamML. We started with Google Scale. We tried to apply it to the typical GCP experience, but it didn't really exactly fit. Understanding your users and building a system for them will be one of the highest priorities to build an efficient platform. Next, you will want to enable your users to focus on what matters most to them. If you're talking about ML practitioners, they will like to focus on building ML-related pieces. Move concerns that are unrelated to their core tasks from your users to your site. Alternatively, you can just use BeamML and let us do the work for you. And what is next for BeamML? So we have so far talked about how we made Beam usable, reliable, and efficient. We have talked about a couple of techniques that we have applied along the way. One of the key pieces that we have talked today was turnkey transforms. Turnkey transforms allowed us to encapsulate these complex use cases and give users single-line declarative syntaxes to handle giant parts of their streaming ML journeys. Next up, what we would like to do is we would like to move from turnkey transforms to complete turnkey solutions. A couple of things that we are working on today is one, real-time recommendations. We would like to give users a chance to combine live data with some historical data and provide this as a single solution. Similarly, anomaly detection. A similar idea, we would like to combine telemetry data with certain historical data, detect anomalies, and offer this as a single out-of-the-box solution. And finally, we would like to build a financial time series index building. A similar idea applies there. We would like to combine current ticks with some historical information and provide information that is applicable and usable in the financial industry. With that, I will wrap up my talk, and here's a couple of resources that you can follow on. First, you can try Beam in your browser today. You can go to that link. If you would like to learn more about Beam and how it's used in production today, you can read more in the case studies section. If you would like to join the community, we would love to have you here. Here are some links. Also, we have a summit coming up in September. Finally, if you would like to play with examples and samples, there are a bunch of documents. Thank you for coming and thank you for listening.
Hello again, and thank you for joining us. I'm thrilled to welcome our next group of speakers, Ken, David, Francis, and Ahmed, to our final Q&A session for today. I really appreciate all of the speakers for taking the time joining us. Before we get into the questions, I'd like to remind the audience that if you can continue to post questions on the @Scale conference link, and we will pull questions from that. So we do have a few questions, and let's get started. So the first question is on the large scale data graph for Ken and David. Could you speak to what was your biggest challenge when building the data graph?
I need to remember to unmute as well. Yes, so I can take that one. Meta has a very big diversity of systems and data processor. And each system has its own idiosyncrasies and are actively worked on by our engineering community. But there are always some corner cases. So gathering the events and being able to deal with all those corner cases can be a challenge as well. Another challenge when building the data graph is to provide a precise measurement of accuracy and coverage for each system. This is very important as we set the bar very high for all our application. And finally, I would like to bring another challenge, a last challenge, which is around the boundary expansion. With the boundary expansion, we are looking at sometimes partial and incomplete information. And merging them together to form a more accurate and complete picture can be a challenge. There's a lot of data analysis, data analytics going on in there. But over time, this really form the backbone of building a complete pictures that is useful for all our application.
Awesome. Thank you for sharing. I guess the long tail of use cases is equally critical as the first 80%. The next question that we have here is, thanks, David. The next question we have here is for Francis. Can DuckDB be used as a data warehouse?
The way I think of a data warehouse is it's really giving you the idea of infinite storage and scalable compute. That's really not what DuckDB itself was designed for. DuckDB was specifically intended to be an in-process, embedded within a single process. I think what MotherDuck does then is try to build enough of that framework around DuckDB so that you can use it for the collaboration, for the scalability that you would get with a data warehouse. So I think that's really where MotherDuck partners with DuckDB and extends its capabilities.
Got it. That makes sense. Thank you. The next question we have here is for Ahmed on the Beam ML. How much of an improvement do you see from GPU efficiency improvement?
Yeah, hi. So we actually see a great deal of improvement. So what we have seen was that I guess there was a lot of low-hanging fruits in this type of workloads where people are mostly focused on getting something out first. We are seeing up to 3x efficiency improvements. We are seeing, when we look at fleet-wide metrics at Google, and we do have a large enough fleet, we are seeing the efficiency improving from lower to 20% to up to 60%. That's incredible in an era where GPUs are hard to get, and when you get your GPUs, you're not utilizing them.
And the abstraction is making it a lot easier, from a usability perspective.
Yeah, that was our goal. So can we get it out of your way so that you don't need to think about it, and we can solve this once and for all for you.
That's awesome. Cool. The next question we have here is on the large-scale data graph. On the policy decision point, what is the interface that it provides for other systems to integrate with?
Yeah, so let me explain. This is a good question. Let me explain a little bit. So we provide both the query-based API and the object-based API. So for query-based API, we mean the service accepts a query and then answers whether the access is allowed or not, and when it's not allowed and why it's not allowed. And we also, for the object-based query, we mean
It accepts a list of objects such as tables and the columns and make the same decision. So we are moving to the direction of increasingly use more and more query-based decision, because query provides higher level context, and the higher level the context and the better and effective decision can be made.
Awesome. Can't wait for when we start integrating this with GenAI as well in the future.
Yeah.
All right. The next question is on for Francis. We hear a lot about Iceberg and Delta Lake. What are your thoughts on those? And does DuckDB support them?
So just, adding some context for folks, those are really standardizing the way in which we're storing the tables in a database, right? And what that does, databases can already read from different file formats, ingest that data. But if we standardize how the data is actually stored, then that's going to let different compute platforms interact with the data in the same way, without having to copy it back and forth and so on. So I think this is a great trend, right? And so DuckDB, I believe, supports Iceberg now, and I think as of the 0.10.3 release, will support Data Lake. So those things are coming along, and I think from a collaboration perspective, data needs to be everywhere, and being able to collaborate and work with different data sources is so critical. I mean, I think this is a great trend. And that's absolutely where we want this next generation of tools to be going, because data without collaboration isn't useful.
Yeah, I agree. I think the glues are, building the glue is important for more standardization. It's awesome. Thanks, Francis. The next question here is for Amit on BeamML. What is the overhead cost of some of the usability features?
Yeah, okay. Excellent question, because you want to know what you're paying for all the conveniences. I guess the truthful answer would be some, in the sense that what we do is nothing more than using the same building blocks in patterns that in an opinionated way that we think that makes sense. There's no overhead of using these patterns and blocks compared to using these blocks directly. The overhead comes from the fact that we make some opinionated choices of making these reliable and better ever handled. And these are the things that, in a system where it's not a production system, one can omit, and they can potentially get a better, efficiently running system. But at the same time, what we see in most production systems, they will be eventually bundled up, and they will not be bundled up in the best, most efficient ways either. Even all of that said, I think we are looking at usually insignificant amount, less than a few percent of additional overhead compared to using these things out of the box without any additional patterns that we provide.
I'm assuming the GPU efficiency improvements kind of,
right, exactly,
more than make up for it.
Yes, it does.
Cool. The next question is for Ken and David. For the iterative discovery, is it human driven? And what is the cycle? How long does it take for each iteration?
It's a great questions. Maybe I can take that one. The data graph already gathers a very large amount of information about our systems and our data flows. But it is very much a work in progress, and we are continuously working to improve both the accuracy, completeness, and the freshness of this data. It is important also to note that we target a pretty high bar in terms of those metrics. And to achieve this bar, we found that we need to keep human in the loop. We do rely on subject matter experts to adjudicate when the confidence is not high enough, and we need this extra help. And we use this information given by our SMEs to feedback loop into our graph and to improve it. But over time, as the data graph continues to improve, both in accuracy and in coverage, we expect that the need to leverage those SMEs will decrease. So for now, it's more like going slow to go fast. And those iteration typically takes a couple of cycles, maybe a few days. Being able to go across the whole graph Really depends on each use case. But it is within the order of weeks at the moment. We really looking to reduce this time and to make it more automatable over time as the confidence and the accuracy improve.
Yeah, that the moving slow to move fast later, that part really resonates. Cool. We have more live questions coming in, so let's keep this going. The next question is for you, Francis. With Mother Duck, when you store the working set data at the edge, as in on the client node, what are some of the security implications you need to deal with?
Yeah, absolutely, right. Data security and knowing where your data is absolutely critical. So I think there's two different sort of things I'd say there. One is, as the data is in transit, as the data is stored, you following your usual expectations of encryption are absolutely important. And then there's also which users, right, are able to access that data. So DuckDB starting, being completely local, didn't really have a notion of different permission models, different levels of access sharing. That's one of the places that Mother Duck is coming in. Right now, we have a very simple permission model where you're able to share read access to your data with anyone or with anyone in your organization. And we'll be building out, more of that as we go, but both controlling who's able to see what portions of the data and then how the data is, stored in transit and at rest.
That's great. Thanks for sharing that. The next one I have here is for Amit on Beam ML. It feels Apache Beam ML is designed to work with data streams. Is there any workaround for data at rest without having to build the plumbing infrastructure to convert the data at rest to data streams?
Yes, there's a workaround. The workaround works out of the box. Frances will love this question because Beam stands for batch and stream, which was a shortened version of both. It actually works with batch and stream pretty coolly. The fault is on me that I was selling the streaming part of it a lot more because I see a lot more, increasingly a lot more streaming use cases. But reality is most of our BeamML customers are actually using BeamML with data at rest. There's a lot more data at rest, and we are seeing increasingly more and more data at rest. And so what they, the person asking this question, what they have to do is literally nothing. The same thing will work for data at rest and streaming data.
That's excellent. Cool. Now a question back on the large-scale data graph. Ken, how do you do row level and column level access control in the metadata graph?
I need to let me try to answer it. So first of all, the column level access control, right? We have integrated with major computer engine systems and passing all the detailed object level information. So for example, for queries that run in the system, that basically when the decision reaches the policy decision point, we know what are the columns being accessed. We actually support even finer and granularity access control than column level. We basically support the subfield level and the access control. And for the row level access control, we supported it for specific certain use cases. And we allow the data to be defined as certain columns to be defined as guarding column and have policies associated with those guarding columns. And so then those policies are evaluated at runtime, and so only certain columns, certain rows can be accessed in those contexts.
Got it. So it's based on the predicates.
Yeah.
That's super helpful. Thank you. The next question we have here is for Francis on DuckDB. What is the sweet spot for DuckDB use cases, and when would you not use DuckDB?
I think DuckDB itself, by being designed to be in memory and embedded in a single process, not aiming to chase the largest data sets, right? Starting from the assumption that many data sets are going to be smaller than the terabytes and petabytes that people sometimes think of when they say big data. Now, as to what the actual limits are in terms of size, I think, DuckDB is at version 0.10.3, right? Still moving towards a 1.0 release, still growing, still improving. So I think we don't have a hard limit there on exactly what, working data set sizes it can handle. But, when people come to Mother Duck, we're telling them on the order of terabytes, smaller numbers of terabytes is something that's totally good for us. Larger than that, we're going to, maybe this isn't the right place to start and to play. So I think that's one thing, right? The data sizes are never intended to be the largest, right? But there is, again, a huge set of use cases that only use smaller sizes. And then I think the other thing is, particularly when you can get those interactive speeds, right? That's where I think DuckDB and MotherDuck really shine, is when you want to have that interactive feel and be able to get those real-time, not just quick results, but results that involve interactivity.
That's great. Yeah, I think most of the time we end up using a portion of the data, and we're working and asking more questions about that set of that data set. Cool. We have more questions. So the next one is for Amit. Can we use Apache Beam on top of Apache Spark or both in parallel?
Yes, you can use it. And if you go back to the data at scale 2017, you will see this graph about how Beam runs on Spark, Flink, and etc. It actually works pretty well. Most of these features works out of the box. And to give a list of customers that I know, for example, Yelp uses Beam ML on Spark. LinkedIn uses Beam ML on Samza. If I remember correctly, Lyft uses Beam ML with Flink, and all of these are, I can talk about here, all of these are public blog posts that you can find and get even the architectural details. The piece that would be different is I've broken this product called Cloud Data Flow, which offers a service. There are parts that these services will differ in certain ways, right? That running Civil Spark means that you will have to go through a different set of configurations. You will have a different set of cluster. At Cloud Data Flow, what we offer is Google's cloud services. So BeamML will work exactly the same, but if there are parts that is dependent on the service provider, how these things are built, what types of hardware you have access to, those things will differ between service providers. But to answer the question here, we have BeamML running on hybrid environments, cloud, on-premise, and with different types of execution systems. It works, and if it doesn't, please find me.
Ton of flexibility built in. Cool. I think we'll maybe have time for the last set of questions. This is back to the large-scale data graph. In the end-to-end workflow, you talked about two types of events. There's the data flow event and the identity-based access events. Could you explain why we needed both?
Yeah, so maybe I can take the first part, and Ken, you can take the second one. So for the first part, each data processors will send events that at a minimum describe what is the source, the target, and also give us a picture about what is the transformation being used. There's also extra information that can be added depending on the system, but these events are very critical to build the final graph in the most accurate and complete manner. So those events for the data flows constitute the backbone of the graph. I'll let Ken provide more details about the identity-based event, which provide a different type of picture.
Yeah, thanks, David. So I think the basically the identity-based event, right? They complement the login-based, because for identity-based, when we don't get to know that all the details and of the transformation, such as what query being run and also the finest granularity, but it actually provides a very high accuracy signal at the coarser granularity, and then which allows us to complement the graph and make the graph complement. Even in some cases, we may not have the fine detail.
So it's like taking a bunch of pictures and then reassemble them into a complete one.
Exactly.
It's a good analogy. Right. The next question here I have is for Ahmed. We have data engineering teams using Java. Is Beam ML limited to Python?
Yeah, okay, that's a great question. I think the landscape of the users significantly shifted over the last 5-10 years in the data engineering space. Like 10 years ago, a bunch of Apache projects were coming out. I think it was all in Java, right? And nowadays, clearly, most of ML projects are in Python, but there are groups of people who prefer different things. And we have a focus on usability. So what we did was we made all these languages work seamlessly in the same type of pipelines. And this may sound like not a useful feature, you're a single person writing a pipeline, but it becomes extremely useful when you have teams that one team is focused on one part of the infrastructure and another team focused on another part of the infrastructure. They have to share, they have to build together. So we made it really easy to build these things in Python and Java and a number of other languages which are more niche that we are supporting. And the other thing that we are seeing, that I've significantly seen this in users, that they go another level of abstract, that they build YAMLs and etc. that even takes the Pythons and Javas of the world and some form of a declarative way of running pipelines. Beam supports that out of the box. So language should not be a barrier. So that's what we are working on by working on the usability.
That's awesome. All right, folks, that's all we have for today. I'd like to thank all our speakers again for joining us, and have a wonderful day.
Thank you, Manju, our speakers, and everyone who submitted the questions in the Q&A session. Thank you, Ahmed, for giving an insightful talk. Next, we will have exciting fireside chat with our engineering leaders, Aparna, Delia, and Manju. And after that, Maur will close out the day. It was a pleasure to co-host this conference for you, and I'm really excited about the fireside chat. Enjoy.
Hello, everyone, and thanks for tuning in. Today, we heard a lot of excitement about how generative AI is forcing a transformation in the landscape of data infrastructure, both within Meta and across the tech industry. I feel inspired by our relentless pursuit and dedication to making a difference, from boosting everyday productivity to solving real-world problems like data protection and risk management. I'm Manju Anand, and I support the Data Infra Storage Engine team that's responsible for all the behind-the-scenes magic for keeping the warehouse data organized, accessible, secure, and performant. And I'm delighted to be hosting this fireside chat with Aparna, our VP of Engineering, and Delia, our tech lead for AI. Would you like to share a little bit more about yourselves?
Sure. I'm Aparna. I've been at Meta for about 8 years. Actually, prior to Meta, I used to work in data as well for, I think, 5 years. So I'm a data person evolved into AI in developer infrastructure too. So my teams really are responsible for all of the software components along this whole data life cycle, like all the way from storing and processing and analyzing data into then training infrastructure and then serving models. And then we have teams that are responsible for all of the developer experience that sits on top of both AI as well as software engineering. So we have teams that are responsible for frameworks like PyTorch, that help enable ML developers, both within the company, but also industry-wide. And we have teams that are working on software libraries and like Hack and HHVM that also, I think, are widely available externally to the industry at large. So it's really a combination of the data and the developer experience and the AI that comes together that makes for exciting times.
Delia?
I'm Delia. I'm a software engineer here at Meta. I started 13 years ago. I have been in data infra all this time. I have always been passionate about AI. So over the last 5 years, I have worked on AI-related infrastructure, including turning up our first GPU AI clusters for recommendation systems, content understanding, and now generative AI.
With what we're seeing now, it just feels like, one of those moments that come by once every couple of decades, maybe once a generation. So I think just across the company, all of us are sort of enjoying the challenges, the opportunities, and solving sort of unsolved problems in some ways.
Aparna, as you said, this is revolutionary and really exciting to be looking at problems that we've not really looked at before. What are you most excited about?
One of the things that I think that's most exciting for me is just the pace of innovation in AI. And, what's state-of-the-art today wasn't state-of-the-art yesterday and won't be tomorrow. And so really dealing with that and growing and evolving with that pace has been interesting for me in many different dimensions. From a technology perspective, I think we're solving problems that very few people in the industry get to see, let alone solve, because we're dealing with scale that I think is somewhat disproportionate. We're just for an example, right? just 2 years ago, we didn't have a foundation model. Today, we have Llama 2 and Llama 3 released in very short amount of time. Mark just announced the other day that we have about 600,000 GPUs in our fleet by the end of the year. And that was a really quick sprint from a much smaller number a couple of years ago. Our AI infrastructure stack was still evolving a couple of years ago, and now we see a really well-articulated stack end-to-end, all the way from data through AI into the developer experience. And one of the things that I think has been interesting is also watching how we work as teams. Because AI is one of those things where it's not just like one team going off and solving that problem. We've really needed to work across infrastructure. Let's start with the data center. The data center has evolved. We have new kinds of liquid cooling technologies that we're bringing into the data center just for AI. Our networking has evolved because training needs all kinds of interesting interconnected machines, because that's sort of like the underpinning of how training works. So our networking stack is evolving. We've got hardware evolution. We just launched our first silicon earlier this year, which I'm really proud about. And it's used for ranking and recommendation, and I suspect that will continue to evolve our hardware roadmap going forward. And we see the software stack co-evolve across data infrastructure, AI infrastructure, all of our underneath like sort of core systems and the developer infrastructure all evolving together in order to solve these problems in AI. And so one of the things that's interesting to me is it's not just sort of the technology stack that's coming together as a fully integrated vertical stack, all working together. It's also how we work within the company. So it takes many people from many disciplines to come together to solve AI problems. We have hardware engineers, co-design engineers, network engineers, and all the way out to the modeling engineers, actually. So one of the things that's been interesting for me is to see how the models are co-evolving along with infrastructure. And I think that's how we get the most benefit, both operational efficiency, but also really gives us the ability to solve hard problems that haven't been solved before. And so if you look at the way that Llama 3 was built, it was very tight collaboration between the Llama 3 research engineers and the infrastructure engineers, co-evolving infrastructure and models at the same time, so we could get to Llama 3 at a record pace. So, so much change, so much change.
I know, Delia, you had a big role to play in bringing all those GPUs to Meta. What are you most excited about?
I think the research and the learning has been just incredible, like out of this world over the last year. Like it's nearly impossible to keep up with everything that's happening in research, in startups, inside the company. And it has really moved very, very fast. Like Facebook and Meta has always moved fast, but this is like redefining moving fast and having everyone, all the teams, the entire company really coming together to push through and build these new models has been super exciting to be part of.
This past year has been pretty wild. We've spun up new efforts, accelerated existing tracks from research to production, while dealing with a surge of demand for hardware. Aparna, what are your thoughts about how things have evolved over the last 18 months?
Yeah, I mean, we have, I think, one of the largest warehouses probably on the planet, like an exabyte scale warehouse. And we've been doing a pretty good job at creating insights for the business and just business analytics in general. And over the last few years, with AI, we see more and more of data being used for AI applications. And if we just start with recommendation systems, we have newsfeed, we have reels, we have ads, and all of these areas have evolved pretty dramatically over the last few years. And you see a confluence of that with GenAI, creating a need for increase in scale, increase in freshness of data, increase in a need for more content understanding as you think about products like Reels. And so systems that we need to go build to derive more understanding of our content. And I think the confluence of all of that has created some really interesting challenges and I think enormous opportunity as well. We also see an evolution of hardware, right? We're dealing with a heterogeneous hardware fleet. And so that has caused us to rethink things around how you place data and how you manage data at scale, which I think is exciting. And I also see an evolution of just the applications within the company of how you use AI internally as well. which has caused, I think, a cultural shift almost, where I feel like the silos are a lot fewer now, just both within the company but also across the industry. And I see teams working together in very interesting ways and merging technologies in very interesting ways to go create this new future.
Delia, we heard Aparna talking about GenAI. What are some of the things that we're doing in data infra for GenAI?
So first of all, GenAI required us to add support for new types of data. Historically, we were working with structured data, schematized data sets in data infra. For GenAI, we had to introduce media, all the way from images to audio to videos and multimodal content, these documents that are interleaving text and images and videos all together. We had to build new ways, optimizations on how we store data, how we process data, such as making video decoding more efficient. We had to build new products for our researchers and ML engineers, from cataloging data to discovering data, exploring data, visualizing data, comparing the data, and creating really out-of-the-box insights for them to make decisions about their data sets faster. Most exciting of all to me has been this transition that we have started from a pure infrastructure team to a content understanding platform where we can build the entire machinery to understand natural language across all the languages of the world, to understand all the types of content, from math to code to very long form text like books and novels, to rapid dialogue, understand what each of these pieces of content is about, understand their language, understand their quality, understand and build various kinds of deduplication and similarity algorithms in order to end up with the highest quality data possible for our researchers and for our models.
Wow, with all those possibilities, I feel our journey is still clearly at 1%. Aparna, in the previous Data at Scale, you talked about redesigning data infra beyond incremental changes. What do you see as the biggest challenge today that requires a redesign?
Yeah, I mean, I think we are maybe one of the unique companies in the industry, Delia, correct me if I'm wrong. I think we are one of the few companies that have a singular data warehouse for both analytics as well as machine learning. And so we're on this journey where we're evolving our warehouse to be able to deal with multiple kinds of, I think, constraints and multiple kinds of requirements. And, counterintuitively, I think having a unified warehouse actually helps us move faster in many ways, but it does come with challenges because we're seeing scale continue to grow 10 to 100x for our data. And we're seeing that along with that scale, we need to also think about flexibility of how our systems process data and use data. And so we've innovated, I think, in so many different layers of the stack. Just last week, we released a new file format called Nimble, which is really optimized for ML workloads. So that's, I think, one of the challenges and one of the evolutions we've had over the last year. One of the other things that's interesting is because we see the pace of AI just continuing to evolve, models are constantly changing, right? We have new model architectures every so often. And so one of the things that we're doing is really looking at infrastructure end to end and developing fully tightly integrated end-to-end solutions, all the way from data centers to hardware to data placement, so we can co-locate data closer to where the training is happening, to serving the models, to our developer experience with PyTorch. And when we not only co-develop all of this internally within infrastructure, but we co-develop our infrastructure along with our models themselves. And so we're able to then find really creative ways around problems because we're building models and infrastructure all together. And I think that's been both an interesting challenge and an opportunity as we've evolved data infra into the world of AI.
Delia, what do you feel is our biggest challenge today?
Some of the challenges I'd like to mention are around the scale of data and the freshness of data. So first, user sequence modeling. This is having recommendation systems learn from all historical interactions our users perform on our platforms. And on product surfaces like Reels or news feeds, in just a couple hours, you accumulate thousands of interactions. So if you go with traditional ways of modeling training data and you have one row in your table for each interaction, you will soon explode the storage. So what we need to do is redesign our data structures on how we model these user sequences, maybe introduce flash, maybe introduce indexing, in order to really unlock the power of data scale at a cost that doesn't break the bank. And I would like to mention real-time graphs. In machine learning, each time you find a new source of data, you keep wanting to try it out until you continue to see, as long as you continue to see wins from it. And graphs are some of our most valuable assets. Our large social graph, our large user interest graphs. These graphs are also used for recommendation systems. They are a major candidate source. So because of that, we are seeing significant wins as we move to real time, and we are continuing to invest in this area.
Yeah, we heard a lot about scale, and we can't only think about scale. We need to think about quality as well. Like a couple of years ago, I feel quality was just one of the design principles, but now it's a must-have to increase our LLM's learning capabilities. Well, there's not enough GPUs in the world to crunch all of that raw data. Delia, what's top of mind for you when it comes to data quality?
Yeah, so you are absolutely right. Quality makes or breaks a model. And we have seen many times in research papers and also in the recent launch of Llama 3, how a smaller model that invests in quality can outperform a much larger model. And we apply different quality algorithms and different quality models for each type of data. So for example, what's a high quality image? It has good resolution. It is aesthetically pleasant. It has a very clearly defined subject. What's a quality video? All the above, because videos are made up of images. But in addition to this is consistency throughout the long duration video, consistency of the characters, consistency of the background, and temporal consistency. And very similarly for text documents or for web documents, identifying duplication and removing it, identifying toxic, not safe for work content and removing it, identifying all the garish content and removing it is super, super critical for the quality of these models. And even more so when you do fine tuning. It's very, very important because there you have millions of rows or maybe even thousands of rows. So every single sample and its quality matters.
Wow, really exciting times. What I love about these events is it actually allows us to peer into what's cooking and imagine the future. Aparna, from a product standpoint, where do you see GenAI helping Meta?
Yeah, we see a lot of applications within the company, and we've applied it internally in data infra. We use it to generate SQL, for example, and English language to SQL, and it's still, I think, in various stages of maturity, but you can start seeing the early wins there, and so the promise of the technology. We use it quite extensively for coding, generating test cases, for writing code, for complementing what engineers do, and I think we're seeing a lot of great feedback from engineers using these products. I'm also excited about just how generative AI can do slightly more complex agentic things. We're looking at areas like being able to mitigate an incident or find root causes of where, what code could cause a particular issue, and slightly more complex things like that. And there's just a ton of exciting work ahead.
Yeah. Thanks for sharing those exciting examples. DJ talked about global impact today, and that made me think about problem selection. At our scale, we need to be really strategic about what problems we solve and how we solve them. So, Aparna, how do we think about research overall? How do we continue to provide the tools to enable cutting-edge research?
One of the things we're all grappling with, I think, across the industry is how do you advance technology at the pace that we want to see it advance, while at the same time doing it safely and responsibly. And I think one of our approaches has been to really double down on open source. So Llama 2 was open source. It's really been great to get all of the feedback on Llama 3 from everyone in the community. And I really see this approach as a potential way that we can continue to improve safety of our models. I do want to say that the open source philosophy is not just limited to our models. We embrace it, I think, across the infrastructure. We've built our AI infrastructure on the Open Compute platform. We still continue to invest in and lead development of PyTorch, which is, I think, the most common ML developer framework out there. And so really across the stack, wherever possible, we are investing in open source. And I think this is going to be a huge lever in how we think about, how we as a society think about how we take these models forward in a safe and responsible way.
Celia, what do you feel about research?
Another area to help research with is data. At some point, not soon into the future, we will exhaust the public data from the internet, which a lot of LLMs of today are using to train. And what do we do then? Synthetic data is definitely picking up. We'll see a lot more of it. And we are looking into building the right tools for our researchers to augment their data and even generate brand new data that follows the same distributions as the real world data.
Yeah, I think one of the interesting things about how this whole space is evolving is that research is evolving too. Today we have LLMs and like large language models as sort of like we're seeing this scaling law continue to hold up. And so, we're working on improving our data scale, our infrastructure scale, all of that together. But over time, I think it's possible that we see other paradigms of research also start to evolve. We have teams working on world models, for example. We have teams thinking about how the brain works and applying our theoretical understanding of the brain towards understanding neural networks better. And so there's all these different paradigms that are developing that I think are interesting. And I can't wait to see how that will affect our infrastructure and the corollaries too as well in some ways. It's interesting to see the evolution there.
Celia, what are you most excited about?
Oh, I'm super excited about applications of science. It would be super awesome to have these educational videos so all the kids can enjoy and study math and physics. That would be super, super cool. I'm excited about these AI models eventually solving open math problems that have been open for tens of years or even hundreds of years. And of course, a lot of advancements in fields like medicine. That would be super cool.
With that promising outlook for the future, I'd like to wrap our conversation for today. I really appreciate everyone joining us this afternoon, and I can't wait to see what we'll cover next year. Thanks for tuning in.
This was an inspiring day, full of learnings from the leading innovative companies in the industry about the challenges and opportunities that generative AI is posing for data infrastructure. Many of us are excited to go and solve these challenges around scale, diversity, quality, and responsible use of data for generative AI. In fact, there is already a lot of progress in the way that data infrastructure is serving generative AI and the other way around, how we use generative AI to solve hard problems in data infrastructure. At Scale is continuing with many more exciting conferences coming up soon, including AI, systems, networking, and more. If you want to stay informed, follow the AtScale website, the YouTube page, and the Facebook page for AtScale. I had a lot of fun learning today with all of you, and I'm looking forward to the next Data at Scale.